Okay. Okay, good evening. Good evening. Can you hear me? So let's get started. Sketch the transfer characteristics. Sketch the transfer characteristics. Given Vz equal to 4.3 volts, VD on is 0.7. Sketch the transfer characteristics. Vz is 4.3 and VD on is 0.7. Find VC at t equal to 1 millisecond, 2 millisecond, 3 millisecond. Okay. So this is an inverting amplifier. What is the gain of inverting amplifier? It is minus R2 by R1. If you remember the gain, it's fine. If you don't remember, you can calculate. Whenever there is negative feedback, the op-amp tries to keep the two potentials almost same. So that is something called the virtual short. So this is ground, so this voltage is almost zero, and the difference is very, very small. That is being amplified, right? So op-amp is basically an error amplifier. It is going to amplify the error difference between the two. For all practical purposes, the voltage at non-inverting is almost equal to voltage at inverting. So this assumption you have to make only when the gain is high. You have to make only when the gain is high, because what is VD? VD is, V0 is A times of VD, and VD is V0 by A, V0 by A. So if A is infinite, then your VD will be zero. But what is VD? VD is nothing but V1 minus V2 is VD. Therefore, your V1 will be equal to V2. So your V1 is equal to V2 only when A is infinite. So never apply virtual short if the gain is finite, right? Okay. So entering current equal to leaving current. So what is KCL? Vn minus 0 by 1K is 0 minus V0 by 2K. So your V0 by Vn is going to be minus 2. So this is of the form y equal to mx. Y equal to mx. It's a straight line passing through the origin. So if you take Vn on x-axis, V0 on y-axis. Now to draw a straight line, 2 points are enough, right? 2 points are enough. So Vn, V0. What are the 2 points on the characteristic? You can take Vn 0 and V0 is 0. If Vn is 0, then your V0 is also 0. What if Vn is 1 volt? Vn is 1 volt. If Vn is 1 volt, your V0 is minus 2 volt. Your V0 is minus 2 volt. So one is 0, comma 0. 0, comma 0 is 1 point. The other point is if Vn is 1 volt, your V0 is going to be how much? -2. So you have 2 points now, and you can draw a line. So this is the transfer characteristics. And how long does it move like this? How long does it move? Till the op-amp saturates. Till the op-amp saturates at plus Vsat and minus Vsat. So to draw a straight line, you need 2 points, right? The 2 points on the graph, if you get, then you can draw a straight line. Now, instead of op-amp saturating at plus Vsat and minus Vsat, can we stop the output at some voltage? Can we stop the output at some voltage, right? To stop the output at some voltage, I have connected Zenars here. So I told you, if Zenars are connected back to back, then what is the behavior of a Zenar? You have 2K here. So this end is at 0, this end is at V0. So it's V0, right? Across 2K. And here you have 2 Zenars. So what is the behavior of a Zenar? If the current flows in this direction, then it is plus minus. You have 0.7 here and Vz. What is Vz given? Vz is 4.3. So 0.7 plus 4.3 is going to be 5 volt. What if current flows in the opposite direction? Opposite, like this. Then plus minus. If the current goes from anode to cathode, it is going to give you 0.7 and this is 4.3. But however, you're going to get either 5 volt or minus 5. So you're going to get plus or minus 5 volt drop across the Zenar. And what is that Zenar voltage? This is nothing but V0. So this is V0 here. So this node is V0. So this is V0 here. And this is 0, 0, 0. So this is 0. So V0 minus 0. So when Vin is positive, this is an inverting amplifier. If Vin positive, your V0 negative. If Vin negative, your V0 is positive because the output is minus 2K by 1K times of Vin. So what happens when Vin slowly increases 0 volt, 1 volt like that, right? If Vin is 0 volt, your V0 is 0 volt. If Vin is 1 volt, your V0 is minus 2 volt. If Vin is 1 volt, your V0 is minus 2 volt. So like that, it keeps on moving, right? Now, what happens at some point, your V0 touches 5 volt, minus 5 or plus 5. Once your V0 touches minus 5 or plus 5, what happens when this V0 touches minus 5? When will it touch minus 5? When your Vin is around 2.5. Around 2.5 because the gain is minus 2. So when Vin touches 2.5 or minus 2.5 volt, your output touches 5 volt. Now, what happens if you increase Vin more than that? If you increase more than that, what will happen if you increase once the Zenar goes to breakdown? The Zenar is also called a voltage regulator. What is a voltage regulator? The output across the Zenar will always remain constant. It will not increase further. So the output is going to stay at this point, at minus 5 or plus 5. It is not going to increase more than that because your V0 is nothing but the Zenar voltage. You can see here V0 minus 0, V0 minus 0 is the Zener voltage. So once the Zener voltage goes to 5, that's it. Excuse me. So once your V0 touches 5 volt, the output is going to get restricted to 5. Now, what happens when the Vin current, the extra current keeps on coming from Vin? This current has 3 paths for it to flow. 3 paths. Now, can op-amp draw current? No, the current is 0. The current is 0. Now, what is the current through 2K? This is constant. Why the current through 2K is constant? Because the voltage across it is constant. So Ohm's law says that if voltage is constant, resistor is constant, then current is constant. So where is that extra current flowing? All this extra current now is going to sink through Zener. Is going to sink through Zener, but this current is almost going to be constant because the voltage across the 2K is 5 volt. It is constant. So any increase in Vn, the Zener will take that extra current, whether it is in the positive or the negative direction. So the output is restricted at 5. The voltage across 2K is also 5. So instead of the output saturating at plus Vsat or minus Vsat, we are able to limit the output. So Zener is also used as a limiter circuit there, right? It's also used as a limiter circuit, right? Zener is used as a limiter. Now, when extra current goes through Zener, what if I put a series resistance? What if I put a series resistance through a Zener? Then naturally when current increases, the voltage will also increase. So your V0 is going to increase now. So in the third case, if you see, in the third case, intentionally I have put 2K here, 2K. So what happens when the Zener is off? The Zener is off. If the Zener is off, what is V0 by V? V0 by V is going to be minus 2K by 1K. This is minus 2. The slope is minus 2. So what happens when the Zener is on? When the Zener is on, the slope V0 by V, slope, this is the slope. Now the slope is going to be minus 2K parallel with 2K by 1K. Minus 2K parallel with 2K by 1K, that is the slope. So 2K parallel with 2K is 1K, 1K, so it is minus 1. So this is a simple way of drawing the characters. Like this, you can have multiple Zeners in parallel, another 2 Zeners with different drop with a series resistor in parallel. Like that, you can pile up any number of Zeners, but the characteristics look simple now. You can take Vn on x-axis, V0 on y-axis. So now we know the characteristics is like this. So once your V0 touches minus 5 volt or 5 volt, the slope here is minus 2. But once it touches 5 volt, the Zener gets on. When the Zener gets on, now there will be a flow of current here. As the current flows, the drop across the 2K will also rise. So your V0 will still rise. But with what slope it is going to rise? It is going to rise with a slope of minus 2. Instead of minus 2 to minus 1. This is minus 2. Now it is going to have a slope of minus 1. It is going to, because the dynamics, the slope is decided by resistor, not by the Zener. Zener will decide only the intercept. If you say y equal to mx plus c, Zener will only decide the intercept. At what point the slope is going to change, right? But the slope is always decided by the resistor value, right? So what is the resistor value that has decided the initial slope, 2K and 1K? But once the output touches 5 volt, then after that, you're going to have a slope of how much? Minus 1. And who is going to decide? It is 2K parallel with 2K. 2K parallel with 2K by 1K. What if you put 2 more Zeners across this say of Vz equal to 9.3 volt. Suppose there's a Zener back to back 9.3. So the slope keeps on moving. Once your V naught touches 10 volt, 9.3 plus 0.7, 10 volt, again you are going to have another slope of 2K parallel, 2K parallel, 2K like that. So like that, you can keep on piling any number of Zenars in parallel like this, and you can get the characteristics, right? So this is a simple way, but you can make it complicated also. Suppose if you say that, sir, I don't want this shortcut, we'll write the Kirchhoff's law. Then you can write the Kirchhoff's law, or you can write a KCL. This is unnecessary. This is unnecessary, but some students want to confirm. It is always better to confirm, but don't do by this method in exam, right? So how will you confirm it? You will write V in minus 0 by 1K equal to 0 minus V naught by 2K. 0 minus V naught by 2K, right? And what is the voltage here? This voltage is going to be 5 plus, for V in positive, your V naught is going to be negative. For V in negative, your V naught is going to be positive. So suppose you want this line. In this line, your V in is negative. V in is negative. So then you are going to have positive voltage plus 5 minus V naught by 2K. So this is the relationship between V in and V naught. So you can have a 2K LCM, 2 V in equal to minus V naught plus 5 minus V naught. So what do you get now? V naught minus 2 V naught equal to minus 2 V naught equal to 2 V in minus 5. Or V naught is 2 V in, 5 minus 2 V in by 2. So some confirmation, okay. So we can substitute now for all V in 2.5. What will happen if V in is 2.5? 2.5. No, this is minus 2 V in equal to minus V naught plus 5 minus V naught. Minus V naught minus V naught minus 2 V naught. 2 V in 2 V in minus 5. So what is 2 V naught here? It is 5 minus 2 V in by 2. So it is going to be 5 by 2 minus 5 by 2 is 2.5 minus V in. So what happens if your V in is minus 2.5? Minus 2.5 into 2 is 5. 5 plus 5 is 10. 10 by 2 is 5. So you can see that this equation is, this point is getting satisfied by this equation. When V in is minus 2.5, your V naught is 5. Then after that you can draw. You can take one more point and draw. You'll get this line, right? It's okay. But this is simple, is it not? This is simple. If you want, you can write by Kirchhoff's law also and do it. Now, what is a simple way now? When the Zener is off, what is the slope M1? V naught by V. The slope M1 is going to be minus 2K by 1K. It is minus 2. It is minus 2. So what happens when the Zener is on? M2 is going to be minus 2K by 1K parallel with 1K. So once the Zener is on, the Zener is in the series arm now. 1K parallel with 1K is 0.5. So it's going to be minus 4. Minus 4. So when will the Zener get on? If you can see here, this is 0. This node is V in. So the open circuited voltage, this is 0. So the complete V in is here. So this time it is not V naught touching 5 volt. It is V in touching 5 volt. It is V in touching 5 volt. So let me draw the characteristics. So we already know the characteristics is going to lie like this. This time, if V in touches 5 or minus 5, 5 volt or minus 5, V in, the slope is minus 2 And after that, after this point, when V in touches 5, the Zener gets on. And after that, beyond that voltage, if you increase V in, the slope is not going to be -2. It is going to be -4. The slope is going to increase. Now, if you don't like it, you can apply Kirchhoff's law, right? Entering current equal to leaving current. And you can get this line, like how we got an equation of a line here. So on this line, we can take 2 points and draw, right? And what is the slope here? Y equal to mx plus c. Here, what is the slope? M1, M2 here, slope. Y equal to mx, -2 by 2, -1. The slope is -1. So if the Zener is off, the slope is -2. If the Zener is on, the slope is -4. The slope is going to be -4. So this time when Vin touches 5 volt, the Zener is going to get on because the Zener voltage is Vin. The Zener voltage is open circuited voltage is Vin. So this is 0. So this node is 0. And here this is Vin and Vin. So Vin is across Zener. So that means when Vin is 1 volt, Zener is off. When Vin is 2 volt, Zener is off. Vin is 4 volt, Zener is off. Vin is 5. Once Vin is 5, the two Zeners, they get on. Once they get on, the slope is not going to be -2 by 1k, is it not? It is -2 by 1k parallel with 1k. So 2k by 1k parallel with 1k is going to be -4. The slope is going to increase after that. Okay, so let us solve this. The switch is open for a very long time. Now it is closed. This is closed at t equal to 0. So assume capacitor initially uncharged. So once the switch is closed, what is the current flowing? What is the current flowing? I is equal to 2.5 minus 0 by 1k. It is 2.5 milliampere. Now this is a constant current. This is a constant current. When a constant current flows through a capacitor, op-amp draws no current. The constant current will flow through a capacitor. The capacitor is going to charge in a linear fashion, is it not? Is going to charge in a linear fashion. Then what is this VC1 and VC2? The total voltage is VC. VC is going to be VC1 plus VC2. All right. So what is VC1 or what is VC2? Both are 1 microfarad capacitors, but across VC2 there is a Zener. Across VC2 there is a Zener. So let us find at t equal to 1 millisecond first. First of all, if a constant current flows through a capacitor, if a constant current I flows through a capacitor, what is the formula for capacitor? Vc equal to 1 by C integral I dt. Current is constant. You can remove it outside the integral. I by C of t. So the capacitor will have a voltage which is having a slope I by C. Is it not? I by C of t. Your Vc is going to be I by C of t. So therefore, Vc1 equal to I by C of t. First, we'll try for t equal to 1 millisecond, 2.5 by 1 micro into 1 millisecond, 1 millisecond. So how much is this? This is going to be 2.5 volt. VC1 is 2.5 volt, right? For t equal to 1 milli. VC2 is also going to be 2.5 I by C of t, 2.5 by 10 power minus 6 into 1 milli. It is 2.5 volt. So VC1 is 2.5 volt, VC2 is also 2.5 volt. But the Zener needs a 5 volt, 5 volt. So the Zener is off. Zener off. Zener off. Therefore, the total VC is VC1 plus VC2 equal to 5 volt. 2.5 plus 2.5 is 5. Now what happens when t is 2 millisecond? This is for t equal to 1 millisecond. What will happen for t equal to 2 millisecond? VC1 equal to I by C of t, 2.5 milli by 1 micro into 2 millisecond. So this is going to be 5 volt. Similarly, VC2 equal to 2.5 milli by 10 power minus 6 into 2 millisecond. This is also going to be 5 volt. So after 2 millisecond, the VC2 here is going to get 5. So what happens once the capacitor reaches 5 volt? Will the Zener keep quiet? Naturally now, the Zener that is off, now it has become on. Zener on. When the Zener is on, what is the voltage across the Zener? Voltage across capacitor is constant. Constant. And VC2 cannot charge further. Cannot charge further. Why VC2 cannot charge further? Because of if it charges, the voltage has to increase. But the voltage cannot increase because the Zener is on. Once the Zener is on, the voltage across the load, the capacitor is now the load, the capacitor is going to remain at 5 volt, right? What happens at t equal to 3 millisecond? So what is total VC? VC1 plus VC2 equal to 10 volt. What happens at t equal to 3 millisecond? VC1 equal to I by C of t. It is 2.5 milli by 10 power minus 6 into 3 milli. That is going to be how much? 7.5. Is it not? 2.5 by 10 power minus 6 into 3. So this is going to be 7.5 volt. 7.5. And what is VC2? VC2 is still at plus 5 volts. VC2 is still at plus 5 volts because the Zener is on. So therefore, VC equal to VC1 plus VC2 is going to be 7.5 plus 2.5. It is 12.5 volt. So when is the Zener? At t equal to 1 millisecond, the Zener is off. So happily VC1 and VC2 are same. At t equal to 2 millisecond, your VC1 is 5, your VC2 is also 5. Still VC1 and VC2 are same, but the Zener is just on. What happens at 2.1 millisecond, 2.2 millisecond? VC2 is not going to increase further. Why it is not going to increase further? Because the capacitor is like this. Here we have connected a Zener. The Zener voltage is always going to be 5 volt. 5 volt. And this is a constant current of 2.5 milli. 2.5 milli. Now the extra current will flow like this through Zener. The extra current is going to flow through Zener. This capacitor voltage will always remain constant. So VC1 will increase, but VC2 cannot increase. Why VC2 cannot increase? Because if it increases, that means the Zener, we are violating, is it not? We are saying that the Zener voltage will increase beyond the breakdown voltage. So that is not possible. Zener voltage will always be 5. So the Zener capacitor voltage will be 5, but VC1 is going to increase now to 7.5 after 1 millisecond. From 2 millisecond to 3 millisecond is going to increase to 7.5, but VC2 is still at 5 volt. So what is the total VC is going to be 12.5. Okay. Yeah, 7 VC2 is still at 5, isn't it? This is 5. 7.5 plus 5. What is 7.5 plus 5? That's going to be 12.5, isn't it? So this is 5 plus 5. 7.5 plus 5 is 12.5. So VC1 is 7.5, VC2 is at 5. The total voltage is going to be 12.5 after t equal to 3 milliseconds. Fine. Okay. Take down. Non-idealities in op-amp. Non-idealities in op-amp. So if op-amp is operated at moderate gain and low frequencies, if op-amp is operated at moderate gain and low frequencies, the practical op-amp almost behaves as ideal. Almost behaves as ideal. But at high frequencies, certain non-idealities come into existence. These are mainly due to the mismatch in the transistors of the differential amplifier. These are mainly due to the mismatch in the transistors of the differential amplifier. And what are they? Some of them are one, input bias current. Two, input offset current. Input offset current. 3 input offset voltage. 4, you can even include finite R in, R naught, and finite gain. Then slew rate, CMRR, the gain bandwidth product. So still the list goes never ending, isn't it? It keeps on going, but these are the areas where questions can be created. Otherwise, simply the voltage, output voltage swing, output current driving capability, everything we can include, but questions cannot be framed, right? These are the areas where questions can be framed. So these are some of the non-idealities in an op-amp. So if op-amp is operated at moderate gain and low frequencies, what did I write? Low frequencies. The practical op-amp, it resembles an ideal model. So if you take a practical op-amp and if you look at the behavior of a practical op-amp, you feel that it's almost behaving like an ideal model, right? So it gives a remarkable agreement with the ideal model. You take an ideal model, you do all sorts of calculations, and then you see a practical op-amp. The practical op-amp almost behaves like an ideal. But if you operate at high frequencies where these parasitic capacitors and all that come into picture, then certain non-idealities will come into existence, right? And these non-idealities, the biggest problem is these non-idealities are impervious. They are impervious even to the curative properties of negative feedback. I told you, negative feedback can solve a number of problems. For example, if you give negative feedback, noise will reduce, distortion will reduce, linearity will improve. There are so many problems in amplifier which can be solved by negative feedback. But these non-idealities, they are so tough that even negative feedback cannot shake them. They will be there. You have to accept it. This is like almost like, this is like getting diabetes or blood pressure. So if you get diabetes and if you go to the doctor will first say, no, don't worry, even I'm also having. And you have to make a certain lifestyle changes such that the person with diabetes and the person with no diabetes, both will resemble almost same. The ideal and the practical op-amp should resemble almost same. So we are not here to remove these problems. These problems will be there, right? They are impervious. They will be there. But the only thing that we can do is we calculate the error and we will see that the error is as small as possible. That is the only thing you can do. We have to see that the error is almost less. It's very, very less, wherein you can neglect for all practical purposes. Are you getting right? So these errors we are going to calculate now. They're very, very small errors, not much. And if you can keep them as small as possible, then we will say that even a practical op-amp is an ideal op-amp, right? So you cannot, there are so many diseases, you cannot reverse them, is it not? So it's something like that, like diabetes is a good example, where you will have to live with that, right? The doctor will give you, a big list saying that even person with 70 years, 80 years, they're still staying with diabetes. So there's no need to worry. You have to make this changes, that lifestyle changes. And then you will also resemble an ideal guy, right? A guy without. So similarly, the input bias current with of an ideal op-amp is almost zero, but the offset current is zero, but a practical op-amp will have some offset. But still, if you see the overall calculation, it almost resembles the same. So we are here to accept them. We are here first to accept these errors. Slew rate will be there. CMRR is never infinite, right? So the gain bandwidth product is not infinite. They are finite, but it's enough for us. For a practical op-amp, it is enough for us to. Okay. So these are mainly due to, I wrote here, these are mainly due to the mismatch in the transistors of the differential amplifier and the reverse saturation currents and all that stuff, right? So no two amplifiers, in spite of so much advancement in VLSI technology, you cannot make two transistors which are exactly same, right? So there will be some sort of a mismatch between the transistors, because of which they are not behaving exactly same. So there might be a certain offset error also, right? So what is this IB and IOS? We know that the op amp, a practical op amp, does draw current. So what is the terminal? What is this plus terminal here? The plus terminal and the minus terminal are nothing but the, see, this is the differential amplifier I told you, and this is your plus and this is your minus, right? Now just tell me, can you design an op amp without base current, right? Can you design an op amp without base current? You can decrease the base current maybe by putting a Darlington pair. If the IE increases, then your IB will decrease. So you can decrease this current, but you cannot make this current through the positive and negative terminal as zero. So a practical op amp does draw current. It is going to draw some current, IP and IN. So now the gate examiner says that if you have a practical op amp that is going to draw a small base current there, then in such an occasion, what will be the error? What will be the error? So let me define this IOS here. The offset current is going to be the difference between IP and IN. It is going to be the difference between IP and IN. And what is IB? It is IP plus IN by 2. So if both are exactly matched, what will happen if IP is exactly IN? Both transistors are same. If IP is exactly IN, then your IOS is going to be what? 0. But that is only a dream, right? You cannot get IP exactly equal to IN. No two transistors are perfectly matched, right? Okay, so let's calculate the errors. But before that, if I say IB equal to IP plus IN by 2, in IES exam, they have asked IP and IN when the examiner gave IB and IOS. So this is simple mathematics. IP plus IN is 2IB. 2IB. And what is IOS? IOS is IP minus IN. Am I right? So IP minus IN is your IOS. Okay. So from here, what is IP? IP plus IP is 2IP. So IP is going to be IB plus IOS by 2. Similarly, IN is going to be IB minus IOS by 2. So these are given in the bits in IES exam, right? If IB and IOS are given, you can calculate IP and IN with this formula, right? So what is IP minus IN? IP minus IN is going to be IOS. IP minus IN is going to be IOS. Okay, so let's calculate the errors now. So now op amp is drawing current because you cannot design a transistor without base terminal. The differential amplifier will have a base terminal, and the base terminal, there will be some current flowing, right? You cannot make it zero. So this is a gate problem. Find V naught error if op amp draws current. Find V naught error if op amp draws current. Now the op amp is drawing current IP and IN. The examiner wants you to calculate the error. Yeah, instead of BJT, if we use MOSFET, then the current is almost going to be, some leakage will be there. You cannot make it zero, but the current is still going to be still small. So MOSFET, if you design a differential amplifier using MOSFET, then your IP and IN are still going to be less, right? You cannot make it zero. Little leakage currents will be there in the device, right? Okay, so in such an occasion, what is your V0? There's a gate problem. Now, generally, what is expected when no input is given? When no input is given, this is ground, your V0 is equal to 0 volts. Are you getting? V0 equal to 0. This is what case? Ideal case. This is ideal case. But can ideal case be possible? No. It's possible only in our dreams, is it not? So this is ground. Because the op amp gain is high, you can still apply virtual short, almost 0 volts there. So you can take some current here, entering current, and there are leaving currents, case here. So tell me, entering current equal to leaving. What is entering current? V0 minus 0 by RF equal to, what is the current in this direction? 0 minus 0 by R1 plus IN, plus IN. So your V0 is going to be IN into RF. So this is given for 2 marks. This is the error. So your V0 is going to be IN into RF. So this is a 2 marks question. So there is always an error, a small offset error output, which is equal to IN into RF. So when we look at this equation, what do we understand? We should start thinking, maybe it puts a higher limit on the value of RF. Because if you keep on increasing RF, what will happen if you keep on increasing RF? Suppose there are 2 designers. One has designed with RF equal to 5K. The other one has designed with RF equal to 50K. So in which op-amp circuit, the error is going to be large, right? The error is going to be large for that op-amp circuit where RF is 50K. Because if RF is more, then your error is also more, right? So it puts a higher limit on the value of RF. On the value of RF. What happens if your RF is 1 mega? Finished. The error is going to be very large. What if your RF is 1 ohm? If RF is 1 ohm, your error might decrease, but the power dissipation will increase. Amperes of current will flow. Right? If your output is 5 volt and your RF is 1 ohm, 5 amperes of current, op amp will go. Is it not? So that is why there's always a trade-off in the design. You cannot make RF mega ohm because the error will be very large. You cannot make RF very small, but the currents are going to be very large. The power dissipation is going to be very large. Okay, whatever it is, this is the solution to the gate problem. This is a solution, right? This is a solution to the gate problem. V0 error is IN into RF. So find V0 if IP is not equal to 0 and your IN is also not equal to 0. So let us take a non-inverting amplifier. A non-inverting amplifier, and the op-amp draws current, IP and IN. Op-amp is going to draw current, IP and IN. So find V naught. Find V naught. Now there are two ways of doing it, right? There are two ways of doing it. One method is if you already know the error. If you already know the error, what is the error? Already you know IN into RF. Then you can apply superposition. You can apply superposition in your mind. What is superposition? You have to imagine that there are two sources now. Two sources. One is the voltage source VIN. The other one is the current source IN and IB. So if you consider voltage source, the current sources are replaced by open circuit. If you consider current source, the voltage sources you can replace by short circuit. So because you already know the error, what you can do, you can directly write V naught equal to with only VIN, it is 1 plus RF by R1 times of V. This is with only VIN, right? Plus VIN, we can replace it by 0 volts. Then with IN and IP, you are going to get IN into RF. This is IN into RF. This is by what theorem? Superposition. So only with VIN, 1 plus RF by R1 VIN, and then IN into RF. So here two things you have to remember. One is the non-inverting amplifier formula, and then the error also you have to remember, right? If you say that, sir, I don't want to remember anything, right? No problem. You can simply apply Kirchhoff's current law, KCL. So what is Kirchhoff's current law? If this is VIN, this voltage is also VIN, and the current entering is equal to the current leaving. The current entering is current leaving. So tell me what is KCL? V naught minus VIN by RF is entering current equal to leaving current VIN minus 0 by R1 plus IN. So this is also, it's simple, is it not? So you can write KCL at that point. Now you are going to get V naught equal to 1 plus RF by R1 times of VIN plus IN into RF. So this, if you see here, who is the actual voltage and who is the error? So this is the voltage here, and this is going to be the error. And this error, we have to keep it as small as possible. We have to keep it as small as possible. So either way, you can either apply KCL or if you remember the formula already, IN into RF from the previous case, right? When no input is there, when no VIN is there, V naught is IN into RF. So you can just take 1 plus R2 by R1 or 1 plus RF by R1 plus IN into RF, which is the error. So the total voltage is going to be this plus error. Now suppose, what is the magnitude of IN? What is the magnitude of IN? This IN will be in nanoampere, is it not? Will be in nanoampere, very, very small, or microampere if you take. If it is, in BJT, it could be microampere. In MOSFET, it is still less. So if IN is 1 microampere and RF is 1K, 1 microampere into 1K, 1 millivolt will be there. 1 millivolt. What is 1 plus RF by R1? Suppose 1 plus RF by R1 is 5 volt. 5 volt plus 1 millivolt. So 5 volt is the 1 plus RF by R1. IN into RF is 1 millivolt. So the error is very, very small. You can still decrease the error if you want. You can still decrease the error. So which is easy? Remembering the formula is easy, or KCL is easy? You can tell me in the comment section, right? Is the KCL easy or remembering the formula is easy? So find V naught. Your IP is not equal to 0 and your IN is also not equal to 0. IP is not equal to 0 and your IN is not equal to 0. If you know the formula, right? Superposition, then what you can do? V naught due to superposition is minus RF by R1 times of V. Am I right? This is the inverting amplifier formula. Plus, if you short the voltage source, then the error is going to be IN into RF. It is going to be IN into RF. This is by superposition. This is by superposition. But if you don't like it, you can apply KCL. So this is also a gate question, right? KCL. So tell me, what is KCL? If this is ground, this voltage is 0, then the current entering is equal to the current leaving. So what is entering current? V naught minus 0 by RF, entering. What is leaving current? 0 minus V in by R1 plus IN. Extra IN has come. 0 minus V in by R1 plus IN. So your V naught is going to be minus RF by R1 times the V in plus IN into RF, which is the error. This is the error voltage. So this is the error, right? Now, I remember in one of the interviews, right, when long back, I was not even a graduate at that point when I joined Viproji. Just after my diploma, I started working. I was basically a repairman. I never knew I will teach one day, right? Okay, so in the interview, the interviewer asked me to draw a non-inverting amplifier. And because I was straight from college, I very loudly, I spoke, I said, I'll have V in here, and there is RF here, and there is R1 here, right? The moment I have drawn this, he said, where is the offset compensation? I said, what offset compensation? I know only two amplifiers. One will give minus RF by R1, the other one will give 1 plus RF by R1. So what is this offset compensation? He ate my brain almost for half an hour. He didn't allow me to go to the next question until and unless I put some resistor here whose value is RF parallel with R1. He said, if you don't put this resistor, then I will not accept the output is almost 1 plus RF by R1. And this is called the compensation resistor. So where is that RF parallel with R1? I said, what is this RF parallel with R1 is going to do? Anyhow, op-amp draws no current, right? Anyhow, op-amp draws no current. So the voltage here is 0. He said, who said op-amp will not draw current? Op-amp is going to draw a very small current, and you have to have some sort of compensation there. Without that compensation, I'm not going to accept that this is a good design, right? Okay, but anyhow, somehow it worked for me in the end, but it was a good learning from me, right? You should always have a compensation resistor there. Fine. Now the question is, because we know KCLs and KVLs now, what happens if I put that compensation resistor in the gate problem? Am I going to decrease the error? So that's what we are going to calculate now, right? So find the V naught error, right? The IP is not equal to 0, IN is not equal to 0, but this time I'm going to put that resistor. What that resistor is going to do after all, let's see. Why this resistor? So this is RF parallel with R1. My interviewer calls this as a compensation, the offset compensation. He says that the error is going to decrease with this because the op amp does draw current. It's going to draw current. So if that is so, then what is my error this time, right? So find V naught error if there is an extra resistor RF parallel with R1. Okay, so let's try. Here you're going to have IP and this is IN as usual. So this is IP, so this current is IP. And according to virtual ground, this V1 is going to be V2. All right, V1 is going to be V2. So let's solve. Let's solve. What is IP? IP is going to be Ohm's law 0 minus Vn by RF parallel with R1. 0 minus Vn by RF parallel with R1. So what is V1 here? V1 is going to be minus IP into RF parallel with R1. And we know that V1 and V2 both are same because of virtual short. So as usual, entering current equal to leaving. So let's apply the same method and let's see why the resistor here is going to decrease the error at the output. So KCL V0 minus V2 by RF equal to V2 by R1, V2 by R1 plus IN, V2 by R1 plus IN. So tell me what is V0 by RF here? It is going to be V2 into 1 plus RF by 1 plus R1. 1 plus RF by 1 plus R1 and plus IN. Am I right? Now in the place of V2, what can I write in the place of V2? In the place of V2, I can write minus IP into RF parallel with R1. RF parallel with R1. Now, what is 1 by RF plus 1 by R1? Can I write 1 by RF plus 1 by R1 as what can I write this? 1 by RF parallel with R1. Is this correct, right? Because the parallel resistor formula is what? What's the R equivalent? It's 1 by R1 plus 1 by R2, right? It's 1 by R1 plus 1 by R2 plus IN. So now you can cancel these two guys here. So then you realize your V0 is RF times of, your V0 is going to be RF times of IN minus IP. Or it is RF times of mod IP minus IN. And what is IP minus IN? It's going to be IOS. IOS. See, I told you, transistors are almost matched. They are almost matched. IP is almost equal to IN. IP is almost equal, but they are not same. They are not same. Imagine you have a current IP which is almost equal to IN and you are subtracting them. You are subtracting them. In the previous case, the error was IN multiplied by RF. But now it is IP minus IN multiplied by RF, where IP is almost IN. IP is almost IN. So when you subtract two currents that are almost same, then your answer is almost zero. They are almost zero. So what is the conclusion that we are going to make here? The conclusion here is your V0 error with compensation resistor is going to be much less than V0 error without compensation resistor. Without compensation resistor. So please, next time you draw a non-inverting or inverting or any amplifier, please don't forget to put RF parallel with R1. RF parallel with R1 should always be there, because the offset error is going to reduce, right? So I've not learned this in the college. Honestly, I've not learned this in the college, but in the interview, and after that, I had to go back and, open the book and watch the compensation and all that. And then I realized, okay, you have to have a resistor whose value is equal to RF parallel with R1, so that the error should be as small as possible, right? So the error is as small as possible now. So now we were able to decrease the error. We were able to decrease the error by connecting a resistor RF. Though a person has diabetes, now he's making some changes, right? So he's taking pills, he's making some changes. And then the ideal op amp and the practical op amp both are going to resemble same. So if you want an ideal characteristics in an op amp, an ideal gain 1 plus RF by R1, then you have to have RF parallel with R1, because the error, the additional error is going to be extremely zero, it's almost zero, right? So you can always neglect for all practical purposes. So let me draw the non-inverting now. Find V naught. Tell me, what is V naught now? If I have this resistor, RF parallel with R1, if I have this resistor RF parallel with R1, then what is the solution now, right? The solution by superposition theorem is going to be what? With V in, your V naught is going to be, or V01 is going to be 1 plus RF by R1 times the V. All right. And what is V02? Error. Error, right? Because of IP and IN here. So now we are imagining that there are current sources, there are voltage sources, and we are applying superposition theorem, right? So this is error because RF parallel with R1 is there. So your error is going to be RF multiplied by IP minus I1, which is IOS. So what is the total V naught? The total V naught is V01 plus V02, which is 1 plus RF by R1 times V in plus RF multiplied by IOS. So if you don't remember this formula RF, then you can always apply what law? KCL and do it, right? So you can always apply KCL. So find V naught. This is the inverting amplifier, the popular inverting amplifier we know. RF parallel with R1. So what is the solution for this? Your V naught is going to be due to V in, it is minus RF by R1 times the V in. Due to IP and IN with the compensation resistor, it is going to be RF multiplied by IOS. RF multiplied by IOS. Or you can apply KCL. You can apply KCL. So if you want to connect anything, please connect it only to non-inverting, right? Don't connect to inverting. Any offset voltage compensation, current compensation, because through inverting, there is negative feedback. So don't mess with the negative feedback structure. Anything that you want to connect, resistors, voltage sources, current sources, anything that you wish to connect for compensation should be at the non-inverting terminal, right? But if you want a negative voltage compensation, you can give minus negative voltage. If you want positive voltage compensation, positive, but give it only to the positive terminal. Don't give to the negative terminal because feedback is there. Where will you connect, right? Now, what is input offset voltage? Input offset voltage, VOS. What is the input offset voltage? If you see the ideal characteristics or an ideal op-amp, an ideal op-amp is going to have a characteristics which goes right through the center, right? This is a tan hyperbolic curve, right? So it goes right to the center, and that operating point here says that if VD is 0, your V0 is 0. Your V0 is 0. If your VD is 0, your V0 is 0. Then you can use this model. Here you can put VD and V0. And if you ground these two, what do you mean by ground voltage? 0. Your VD is 0. Then you can say V0 is 0. So this triangular model, it fits the characteristics. This model fits the characteristic. But it so happens that this characteristics, as I told you, is only a dream. Is only a dream. Definitely, you can't get exactly in the middle. Through non-inverting and inverting, there's some small millivolts, you cannot exactly expect 0 because of the mismatch in the transistors of the differential amplifier. You can see that when I started, I told you there is a differential amplifier. Am I right? So how do you bias a differential amplifier? Yeah, this is a differential amplifier. Can you see here? Can you see that you have a differential amplifier? It is biased by some current mirror here. And can you, by connecting here plus 12 and minus 12, such a large voltage, do you think with all the drops here, here, this potential will always be 0? At least a millivolt will be there, right? So you cannot expect 12 and minus 12 to be given, but still the base potentials are 0, right? A slight mismatch will definitely be there. When there is a slight mismatch in then what sort of characteristics you can expect? You cannot expect this characteristics. A practical op-amp is going to give you a characteristic something like this. Something like this. Suppose this is 0. This is a minus 2 millivolt. This is minus 3 millivolt. This is minus 1 millivolt. This is 0, something like that, right? So this says that when your VD is, if your VD is minus 2 millivolt, then your V0 is 0. If your VD is minus 2 millivolt, then your V0 is 0. Okay? Then what sort of model will you draw? What sort of model will you draw such that because we know the characteristics of the what you call op-amp, the op-amp equation is always V0 is A times of VD. Am I right? V0 is A times of VD. Or A times of, you can say what is A times of what? V1 minus V2. All right, A times of V1 minus V2 or A times of VD. So what changes will you make in the model? The changes that you have to make in the model is, because here the voltage is minus 2 millivolt, what if you give plus 2 millivolt in the model? See, we are not externally connecting to an op-amp. Op-amp, we are not going to do it. We are going to apply this model for calculation. Because some students say that, sir, are you giving that voltage? I'm not giving it. I'm buying an op-amp and I'm using it in my analysis. If there is some offset here, I'm going to draw it on a piece of paper such that my calculations are going to match with the practical calculations. Otherwise, the practical calculations will cheat me. My theoretical calculations will be different and my practical calculations will be different. If my practical calculations, which I see, and what I do on paper should match, then I have to include this extra 2 millivolt. So what happens if I include this extra 2 millivolt here? If I include this extra 2 millivolt, then we know that this node is going to be V1, this node is going to be V2. And this node is going to be V1 and this node is going to be V2. Now just tell me, what happens if you give minus 3 millivolt? If you give minus 3 millivolt, you're going to get minus VSAT. If you give minus 1 millivolt, you're going to get plus VSAT. If you give 0, you're going to get plus VSAT. But if you're giving minus 2 millivolt, your output is going to be 0. So if I give VD here, if I give VD, this is my VD, of minus 2 millivolt or say minus 3. So minus 3, I'm giving minus 3. And let me apply KVL here, right? So let me apply KVL. So what do I get? This is my VD. What do I get when I apply here, right? So this is 3 millivolt minus VD plus 2 millivolt equal to 0. 3 millivolt minus 3, right? This is minus 3 millivolt I'm applying between V1 and V2. So it's minus 3 plus of minus VD plus 2 millivolt to 0. So what is my VD here? My VD is going to be, because of the minus 3 millivolt, your VD is going to be minus 1 millivolt. So your VD is minus 1 milli, V0 is AVD. With VD minus 1 millivolt, it is going to be minus VSAT. It is going to be minus. So with minus 3 millivolt, it is at minus VSAT. What if this is minus 2 millivolt? Already I have put 2 millivolt here, minus 2 millivolt plus 2 millivolt, it's going to be 0. If VD is 0, V0 is A times of 0. So your V0 output is 0 volts. So if you give VD of minus 2 millivolt, your V0 should be 0. That means what compensation will you include in the model? The compensation should be exactly reverse of this VOS value. What is the reverse here? If it is minus 2 millivolt, you have to put an additional plus 2 millivolt here, right? You have to put an additional plus 2 millivolt such that this characteristics is going to obey. This characteristics is going to obey. Okay. See, whatever it is, I'm just telling you from the characteristic. The examiner will already give you a compensated voltage 2 millivolt, 3 millivolt. You directly connect and calculate. You directly. But what I'm trying to say is, if there is a positive value, that means the characteristic has shifted left. If there is a negative value, that means the characteristics has shifted right. Because characteristics can also be like this also, right? If the characteristics is like this and there is a positive value here, then you have to put an additional negative voltage here. Are you getting right? Okay. So whatever it is, the examiner will give you, so you don't have to worry about it. So the examiner will say, if your VOS that you want to connect is some value, say 2 millivolt, right? Find V0. Find V0. Right. This is V. This is 1K, 2K. No. And here you have to include a VOS of 2 millivolt. 2 millivolt. This is V. Now what will be your V0? Wherever he asks you to calculate it, To the non-inverting, you have to give a positive VOS. So VOS is given by the examiner. If he gives positive, write positive. If he gives negative, write negative. But if he has given positive, that means that op-amp characteristics was shifted negative. If he has given negative, that means the op-amp characteristics is shifted positive. So you don't have to worry. He's already giving you, just connect that and calculate, right? So what is your V naught now? V naught. Your V naught is going to be how much? 1 plus RF by R1 times of V. It is going to be 1 plus RF by R1 times of V due to V plus short the voltage source due to Vs. It's going to be 1 plus RF by R1 times of VOS. It is going to be 1 plus RF by R1 times of VOS. Or it is 1 plus RF by R1 times of V in plus VOS. It is going to be V in plus VOS, right? So your VOS will always be there, right? Your VOS. Or you can do one thing. What if nothing is given? Nothing is given, right? If VOS is not equal to 0 and your IP is also not equal to 0 and IN is also not equal to 0. If your IP is not equal to 0 and your IN is not equal to 0. There is RF here, R1 here. What is V naught? What is V naught? Your IP is not equal to 0. Your IN is also not equal to 0. What is V naught? So to solve it, what is the change we are going to make here? This is the op-amp. Connect VOS only to the positive terminal, always. Here there is RF and R1. That means what? We are trying to alleviate the problem one by one. Are you getting, right? If the examiner says, what is the error due to current offset and voltage offset? Then, see, that is why I give you this analogy, right? It's like when you visit a doctor and you tell him 4 problems. If you tell him I have BP, I have sugar, I have diabetes, right? I have a headache, I have fever. The doctor will apply superposition theorem on you. The doctor is going to give you 1 pill for fever and 1 pill for diabetes and 1 pill for blood pressure. And finally you mix them and you have them, right? But if you have them one by one and then drink water one by one, or if you take all of them and then drink, if your body is like the superposition, right, the linearity property, then the effect is still going to be same. So all the errors are there, but we are going to alleviate the problem one by one. We are going to take the problem one by one, and the errors are going to get added now. The errors are going to get added. So if there is only VOS, what is your V naught? Your V naught is going to be 1 plus RF by R1 times the VOS. But if op-amp also draws current, IP and IN, and there is no compensation resistor, when there is no compensation resistor, you have to add and say it is IN multiplied by what? RF. What if there is a compensation resistor? Then you will say RF multiplied by IP minus IN, which is IOS. Are you getting? So if your VOS is not equal to 0 and your IP is not equal to 0, IN is not equal to 0. So now 2 errors we have included. One is the current offset, the other one is the voltage offset. Slowly we'll have slew rate and CMRR. So you keep on adding them, plus slew rate, the error due to slew rate, plus the error due to CM, plus the error due to this, plus error. So if you add up all of them, 0.1 millivolt, 0.2 millivolt, 0.3 millivolt, 0.5 millivolt, finally it will come to 1 millivolt like that. So that error you have to keep as small as possible, right? Okay, so how do you find V naught if your VOS is not equal to 0, IP is not equal to 0, and IN is not equal to 0, and you still have a compensation resistor? Suppose you have a compensation resistor here, RF parallel with R1. Then what is your output? What is your output? And your VIN is at inverting also. What is your output? There's IP here, there's IN here, and there is also a small VOS here, right? So how many sources are there? Superposition theorem, how many sources? One is the big source Vin, one is a big source Vin, and then two chota sources. One is the current, the other one is the VOS. So three terms you're going to find in superposition. Three terms in superposition. So tell me, let's respect Vin first. So due to Vin, there's an inverting amplifier. So it's minus RF by R1 times the V. Plus, due to the current offset with a compensation resistor. With the compensation resistor, it's going to be RF into IOS, IP minus IN. Plus, with VOS, and I told you VOS should always be connected to the non-inverting. So it's going to be 1 plus RF by R1 times of V, or VOS. So now you remove currents here and short voltage source. Only VOS is there. So it's going to be 1 plus RF by R1 times the VOS, right? So now these two are errors. RF into IOS is the error, and 1 plus RF by R1 into VOS is also the error. Given find V naught if IP equal to 2 microampere, IN equal to 1 microampere, IP equal to 2 microampere, and IN equal to 1 microampere, and your VOS equal to 0 volts. Your VOS equal to 0 volts. See, VOS, we are not going to physically connect. VOS is only for calculation purpose, right? We are not going to physically RF parallel with R1 we are connecting. VOS, we don't connect a millivolt signal to op amp while doing it, right? We are just going to model an op amp by connecting that voltage, and by doing calculation, our practical op amp values are going to match with the theoretical values. See, otherwise you do something on paper, you get 5 volt. But when you go and see in the lab, if it is 6 volts, then what is the point? In engineering, the biggest thing is what? Predictability. Whatever experiment you conduct, even before you conduct an experiment, you should be able to predict the values. If your values are not matching with what you do on paper, there's no meaning. But when will it match with what you do on paper? If you put an extra VOS on paper, so that is only, we have to include in it a model. But if you physically connect that voltage, are you compensating it to 0? Yes, you can do it. But who will give you a millivolt signal? Yes or no? These days, op amps are come with internal compensation. They are coming with internal compensation. They will compensate it, right? You are not going to externally do it. Externally 2 millivolt signal, we are not going to connect, right? You're just going to buy an op amp and use it with that error. So that for calculating that error, you have to put an extra VOS at the non-inverting, because we have seen that minus 3 millivolt, when you give, the output shifts to minus VSAT. If you give minus 1 millivolt, minus 1 milli plus 2 milli, 1 millivolt, V0 is AVD, your output will shift to plus VSAT. Are you getting? It's only for calculation purpose. Okay, so how are we going to solve this? Now this circuit we have already done in the class. This is R1 in our class, this is R2, this is R1, and this is R2. And I proved that this is V1 and V2, V1 and V2, right? So I have proved that your V0 is going to be R2 by R1 times of V1 minus V2. So it is going to be 10K by 1K times of 3 minus 2, which is 10 volt. This is 10 volt, right? Now what is V0 error? For V0 error calculation, short circuit the input voltages, apply IP and IN now. IP and IN. This is 10K. 2K and 10K are in parallel. If you short 3 volt here, 2K and 10K are in parallel. Sorry, 1K. 1K and 10K are in parallel. And here there is 1K and 10K here. This is 1K and 10K. So luckily, the 1K and 10K, they are going to be the compensation resistor for this. So what happens when IP and IN, whether you have an IP here, you have an IN here. What is going to happen? Your V0 error is going to be, it is going to be RF multiplied by IP minus IN or IOS. Who is RF here? RF is, oh, what is this guy here? This guy is 1K. This guy is 10K. Yeah, 10K. So there's 1K and 10K. So it's going to be 10K into IP minus IN. What is IP here? IP is going to be 3. IP is going to be 2 micro minus 1 micro. 2 micro minus 1 micro is 1 micro. 1 micro into 10K. 1 micro into 10K is going to be 10 millivolts. 10 millivolts. Now, therefore, total V0 by superposition is going to be 10 volt plus 10 millivolt. It is going to be 10 volt plus 10 millivolt. It's going to be 10.010, right? 10 point. So the error is quite small, right? It's 10.010 volt. And this 1K and 10K, they are like RF parallel with R1. They are acting like a compensation resistor now. So the difference amplifier already has this compensation, right? The beauty is whenever you have a difference amplifier, these two 1K and 10K are going to act like a compensation resistor now, right? So it is RF multiplied with IP minus IN. RF multiplied with IP minus IN. The open loop gain of op-amp is A. The gain is 100. B, the gain is 10 lakhs. 10 lakhs. Find V naught. Find V naught. If VOS equal to 0.3 millivolt. If VOS equal to 0.3 millivolt. If VOS equal to 0.3 millivolt. Okay, so this is a gate problem. This is a gate problem. So what is the solution for this? A practical op-amp, even if you ground both the terminals, there is going to be a small VOS here, VOS. See, this is the reason I told you, if you remember, students were asking when I started op-amp, they were like, sir, when will op-amp saturate? When will it not saturate? The answer is, op-amp will always saturate. Even if both the terminals are grounded, see here, both the terminals are, it is going to saturate. You take a practical op-amp, non-inverting you ground, inverting you ground, and see the output, it is saturated already. So an effort has to be put to pull that output to linear region, that is with negative feedback. So a student should always ask how op-amp will not saturate. He should not say when op-amp will saturate. It will saturate come what may, even if you don't give any input. Even if you don't give any input, see here, there is always a VOS here. There is A here, your VD. Your VD is nothing but VOS. So what is V naught? V naught is A VD. It is A times of V1 minus V2. It is A times of V1 is a voltage at non-inverting, V2 is a voltage at inverting, V1 minus V2 is VOS minus 0. It is VOS, A VOS is V naught. So, if op-amp has moderate gain, then it will not saturate. If op-amp has high gain, pakka it is going to saturate. The examiner has given A 100. I am giving a practical op-amp A 10 power 6. See what happens if A is 100, right? If A is 100, then your V naught is going to be 100 into 0.3 millivolt, 0.3 millivolt. So what is 0.3 into 100? 0.3 into 100 is going to be 30 millivolt output, 30 millivolt. So the error is quite small because the gain is small. Now, what happens if A is 10 lakhs? Then your V naught is going to be 10 power 6 times 0.3 milli, 0.3 milli, which is 3 into 10 power minus 4, right? 3 into 10 power minus 4. So this is going to be 300 volt. Can you get 300 volt output? No. The op amp output is going to shift to plus Vsat. So it is going to shift to plus 10 volts. Saturated. So even if you don't give any input, your output is always going to saturate if it is a practical op amp with high gain. But as long as you work at moderate gain and low frequencies, even if there is a certain non ideality, still it is acceptable, right? 30 millivolt is okay, acceptable, but 300 volt, right? So the output is going to shift to plus 10. You cannot get 300, so it's going to shift to plus 10 volts at the output. So this is the explanation, right? See, somebody has to come out with an explanation, right? If I simply say, no, you ground both, the input output will saturate. Then student will ask, what is the explanation on paper? On paper. Then we have to write like this. Even with no input, there is a VOS in millivolt. Op amp gain is high. Your output is going to be that millivolt signal multiplied by the gain. It is going to saturate. So that is why we need this model, VOS. This model is like fulfilling, right? Because of this model, I can come out with an explanation that the op amp is saturating, right? So similarly, with this model, you can come out with an explanation why why the integrator that I've explained in the class will never work, right? The integrator that we have explained in the class is never going to work in the lab, right? That's not a practical integrator. What is the reason behind it? The integrator that we have discussed in the class is never going to work for the reason that if I connect a capacitor here, right, and I'm applying Vin, right, now, or Vin of t, I said your V0, how did we do this? If you remember, we have done by the frequency domain analysis, right, frequency domain, and I said V0 of S by Vin of S is going to be minus 1 by SC by R. It's going to be minus 1 by RC of 1 by S. And wherever 1 by S is there, this circuit is an integrator, right? Is an integrator, right? Now why this integrator does not work? Why this integrator does not work? So somebody has to come out with an explanation, right? So what explanation will you give? So the explanation is like this. The explanation is, let's calculate the error even without input. Don't give any input, right? Don't give any input. This is grounded. Now, a practical op amp will have some VOS here. VOS. This is R and this is C. Now, what is your V0 error? What is your V0 error? Right? V0 error. So tell me, according to virtual ground, this is going to be VOS. Am I right? Then the entering current is equal to the receiving current. So what is the current I here? What is the current I? I is going to be 0 minus VOS by R or minus VOS by R. Am I right? Then what is VC? VC. VC is going to be 1 by C integral I dt. VOS is constant, R is constant. It is I by C of t. It is I by C of t. So it is going to be minus VOS by RC of t. minus VOS by RC of T is your VC, is your VC. Now what is V naught? VOS minus V naught, VOS minus V naught is VC. VOS minus V naught is VC. Or what is V naught? It is VOS minus VC. It is VOS minus VOS, minus of minus is plus, by RC of T. Now, please see here, no input is given. This is a function of time. That means what? Don't give any input. Switch on. You go have a cup of coffee and come. What will happen? When you go, just, after 4 millisecond, 5 millisecond duration, when you switch on, because of this offset, the capacitor will continuously charge and charge and charge and charge and charge and charge. As time progresses, your V naught is increasing. So what happens at T equal to infinite? What do you mean by infinite time? In analog, infinite time means what? Like hardly 5, 6 millisecond, 10 millisecond. So at T equal to infinite, your V naught is going to be at plus Vsat. So your output is going to saturate at plus Vsat. It's going to saturate at plus Vsat. That means even without input, forget about circuit behaving as an integrator. Because once the op-amp saturates, you cannot bring him back to the linear region. If it's 12 volt, that's it, it's 12. You give an input, you don't give an input, it's 12, so that's it, it's going to be 12, right? Then where is the question of integration? There's no question of integration at all, that even without input, your output is going to saturate, right? Then how are you going to design? So this is what you call this explanation of VOS, modeling of VOS is soothing for us, right? It somehow gives us an explanation that why this integrator does not work. Why this integrator does not work? Because there's definitely a small amount of VOS there, because of which the capacitor keeps on charging and charging and charging and charging. And even without input, your output is going to saturate. Okay. Then how are you going to design a practical integrator, right? A practical integrator. A practical integrator in the lab is always going to be having a resistor in parallel to the capacitor. In parallel to the capacitor. Now, you might say that, sir, this circuit we have already done. This is a low-pass filter. This is a low-pass filter, and now you are saying that this is an integrator also, right? Let's see. What is V naught by V? V naught by V of S is this. I'll treat it as Z minus Z by R. Minus Z by R. What is Z? It is RF parallel with 1 by SC by R. It is RF into 1 by SC by RF plus 1 by SC. So your V naught of S by V in of S is going to be minus RF by R by 1 plus SC RF, or minus RF by R by 1 plus S can be written as J omega CRF. J omega CRF. Now, where is the integrator here? Where is the integrator here? Because for an integrator, you should have 1 by S, right? But here there is some factor, minus RF by R by 1 plus SCRF. Now, tell me, case one. If your omega CRF is much greater than 1, suppose this factor omega CRF is far greater than 1, or omega is far greater than 1 by CRF. What happens if omega CRF is far greater than 1? Then your V naught by Vin is going to be minus RF by R, minus RF by R1. Then the circuit is what? If this factor is much greater than 1, then the circuit is an inverting amplifier. The circuit is an inverting amp, minus RF by R by 1 plus SCRF. So omega CRF. So for high frequencies, what happens is this high frequency or what? Omega CRF minus RF by R1 by minus RF by R by 1 plus SCRF. So what happens for low frequency omega 0? For omega 0, it is going to be this. So let me change this here. If this value is much less, if this guy is much less, then the circuit is an inverting amplifier. Or omega is less. Omega is less means what? It is an amplifier for low frequencies. Amplifier for low frequencies or a low pass filter. What is a low pass filter? A low pass filter is an amplifier for low frequencies. It is amplifier for an inverting amplifier for low frequencies. So this is a low pass filter we have done in the class. It's correct. But what happens at high frequencies? At high frequencies, you don't get gain. You don't get gain. Your omega CRF is much greater than 1, or your SCRF is far greater than 1. Then what is your V0 by V? Your V0 by V is minus RF by R by SCRF. Your RF gets cancelled. Minus 1 by RC of 1 by S. All of you, what is this minus 1 by RC of 1 by S? Can you see here? What is this minus 1 by RC of 1 by S? That means the circuit is behaving as an integrator. So it's an integrator for high frequencies. For high frequency, first of all, gain will not be there. But even at the low gain section, it is still behaving as an integrator where your omega is much greater than 1 by CRF. So what is the summary here? What is the summary? This circuit is an integrator, and this circuit is also an amplifier for low frequencies, which is a low pass filter. Then how it is going to do both the operations? How is going to do both the operations for low frequencies? For low frequencies, it is going to act like a LPF or an amplifier, right? For high frequencies, it is going to act like an integrator. So what is the transition here? Your omega should be far, much greater than 1 by CRF, or your omega is much less than 1 by CRF. Omega is greater than 1 by CRF. So this is an integrator only for what frequencies? For accordingly, you can adjust the value of R and C. See, the main intention is what? You know what signal you have to integrate. Then accordingly, you design the value of what? RF and C in such a fashion that the omega value that you are giving is much greater than 1 by RFC, so that it will behave like an integrator, right? So you can adjust the values of R and C. Okay, shall we take a break now? We'll take a break. When we come back, we will see more of this. Okay. Is my voice audible? Take down. Slew rate of an op-amp. Slew rate of an op-amp. It is the maximum rate of change of output voltage. It is the maximum rate of change of output voltage for all possible input signals. For all possible input signals. So slew rate is given as dV naught by dt max. And the units of slew rates is in volts per microsecond. It is in volts per microsecond. So slew rate by definition is the maximum rate of change of output voltage for all possible input signals. Now, how to calculate slew rate or how to find slew rate, right? How to find slew rate of an op-amp? It is the maximum rate of change of output voltage for all possible input signals. Now, you can take an amplifier or you can take the best amplifier or the worst case amplifier. What is a worst case amplifier which has got the maximum loop gain? The worst case amplifier which has got the maximum loop gain is buffer. Unity gain feedback is the circuit with the maximum loop gain. Because if this is A and beta is 1, A beta is A. But if you have RF here, R1 here, then your beta is going to be R1 by RF plus R1. Beta value will be 1 or less than 1. So the loop gain A beta is A into beta. So beta is 1. So this is the buffer is the circuit with the maximum loop gain. Now for this buffer, what happens if I give a step input? A step input. Intentionally I am giving a step input. A step input is called the, what do you call a step input? It's the Heaviside test signal, right? It's the Heaviside step input. This is called a test signal. A step input is called the test signal. So why do we apply this test? To know how fast the op-amp will run, right? Because op-amp has to take the current from the supply and then backtrack and then calculate the error. He has to make the error 0. And then the voltage at non-inverting will appear as voltage at inverting. So he needs some time to do it, but inside you have a what you call parasitic capacitors. You have a lot of parasitic capacitors here, and capacitor will not allow sudden changes. Capacitor will not allow sudden changes. So when there is a sudden change here, where the input is rising from 0 to say 5 volt, 0 to 5 volt, what will be the output? The output takes some time to slew from 0 to 5. It is slewing from 0 to 5, takes some time to slew from 0 to 5, maybe in a time 0.1 microsecond. In a time 0.1 microsecond. So what is slew rate? Slew rate is going to be 5 volt in 0.1 micro. That is going to be 50 volt per microsecond. So this is the maximum speed. So to calculate the maximum speed at which the op-amp can run, you have to apply a test, a challenge, where the signal just runs in a flash, right? So like 0 to 5. Suddenly, an op-amp cannot take up this challenge, so he'll naturally give you an output that is kind of having a slope like this. Then this line, you can easily calculate the slope, is it not? dV naught by dt. What is expected now? Slew rate for an ideal op-amp. What is the slope of a line parallel to y-axis? Slope of a line parallel to y-axis should be infinite, but this is only an ideal case. So this is our practical op-amp. A practical op-amp always has a slew rate which is finite, right? 50 volt per microsecond is the slew rate. What happens if that slews from 0 to 5 in 0.01 microsecond? 0.01, it is going to be 500 volt per microsecond, right? So at that speed, it's not that it has to slew to 50 volt. At that speed, it is going to switch the output, right? Now, with this good piece of information, how you can avoid distortion? How you can, with this value, how to avoid distortion? With this value, right, in mind, how to avoid distortion. So it's simple. Anytime you give an output dV naught by dt for all sinusoidal input or for all sinusoidal output should be less than or equal to the dV naught by dt max, or the slew rate should always be less than the slew rate of op-amp. So next time you want to give any sine wave or triangular wave, see that all the sinusoidal input which gives a sinusoidal output should always have an output value whose value is less than the dV naught by dt max. Suppose by applying this test, we got 50 volt per microsecond as a slew rate. Suppose you have given two sine waves. One sine wave slews at 40 volt per microsecond. There's another sine wave that wants to slew at 60 volts per microsecond. Out of these two, which will have no distortion and which will have distortion? See, the maximum capacity of op-amp is 50 volts per microsecond. That means, see, it's something like the maximum capacity. Suppose the maximum capacity for my son is to write 2 pages of homework. Suppose, right? His maximum capacity is 2 pages of homework, which I know. Now, 2 teachers have given him homework. One teacher has given him 1 page of homework. The other teacher has given him 5 pages of homework. So one teacher 5 pages, the other teacher 1 page. So which one will he successfully reproduce the signal, faithful reproduction? Which one is going to be, distorted, right? Distorted in the sense like he's not going to do that homework properly, right? So it's understood that 1 page he can successfully do, 5 pages he cannot, because his maximum capacity as a parent I know is only 2 pages, right? So similarly, you can give any sine wave that you want, but the slewing speed of a sine wave, this is a sine wave. What is slewing? Tuck, 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 tuck. This is slewing, right? So when from the supply, you're going to produce that sine wave, the slewing speed of the sine wave should always be less than its maximum capacity for no distortion, right? Okay. Now, if you ask me, what is the slew rate for sinusoidal signals? Slew rate for sinusoidal signals. Slew rate for sinusoidal signals. If your V0 is Vm sine omega t, what is dV naught by dt? What is differentiation of sine? Differentiation of sine is going to be cos omega t, Vm, and with respect to t, so you can multiply omega, right? Now, what is dV naught by dt max? What is the maximum value of cos? It's 1, so it is omega Vm. So this is your slew rate, right? And what is omega? Omega is also 2 pi f or f max v max. Vm is v max, right? So 2 pi f max v max is the slew rate. Now, so what I'm trying to say is, even in a sine wave, where you want to calculate slew rate, because if you say that, sir, I'm having a sine wave and the sine wave slews here with some slope, there's a tangent, right? There's a tangent here, there's a tangent here, right? So there's different slopes here, right? But from where you will calculate for a sine wave? For a sine wave, if you want to know the slew rate of a sine wave, and this slew rate of sine wave should be less than the maximum capacity of the op-amp, the maximum capacity which you applied the step input. But even in a sine wave, where will you calculate? Tell me, in a sine wave, where is the maximum slope? The maximum slope is not here. The slope here is 0. The maximum slope is at 0 crossing here. Zut like that. The signal, it just goes zut like that, right? So this is the maximum slope, right? So what is 0? At 0, cos 0. What is cos 0? Cos 0 is going to be 1, right? So when you differentiate here, you're going to get cos. The maximum value of cos is going to be 1. The slope is maximum at 0 crossing. So a sine wave is going to have a maximum slope at 0 crossing, right? Okay. So 2 pi f max v naught max. So this slew rate of signal output should be much less than or equal to slew rate of the op-amp. How do you find slew rate of the op-amp? From the step input, right? Examiner will give you. You don't have to worry. You are not going to apply step input. If you want to find slew rate in the lab, how will you find? You apply a test, a step input, and then find, right? So slew rate for sinusoidal signal output should always be less than the slew rate of op-amp for no distortion. No distortion. No distortion. So slew rate is a function of frequency and amplitude. So what do you mean by that? That means it puts a limit for the designer on the amplitude as well as the frequency. Frequency means number of waves per second. Amplitude is the peak, right? Vm is the peak. So if you have a sine wave that's having high frequency but less amplitude, and if you have a sine wave that's having high amplitude but less frequency, but if the product is same, the challenge for op-amp is the same, because slewing means what? It's like tuck 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 tuck. So how that tuck tuck moves, it depends. Where it's going up and down or going, sidewise like this, right? So it's all depends on how you're slewing, right? So you're slewing like this, tuck tuck tuck. That means it is amplitude, right? If you're doing like this, it's more frequency. But if the product is same, then it's the challenge for op-amp is the same, right? But don't make op-amp to slew for high frequency and high amplitude like this. If you want op-amp to do like this, then pakka distortion will come, right? So this should not be there. High amplitude and high frequency. See, it's not only op-amp. The slew rate is like what? I don't know. It's like in physics, we say something called the inertia, right? What is the law of inertia? Right. So the law of inertia says that everybody wants to be in that state of rest, right? So it doesn't want to change suddenly. So similarly, here, electronic guys, electronic engineers, we claim that all our amplitudes are in millivolt, right? So, and all our frequencies in gigahertz. If you see, if you ask, what's the frequency in the speed in electronics, we say 1 gigahertz, right? An electrical engineer will get worried. 1 gigahertz, such a big frequency. How much amplitude is there? We'll say 1 millivolt. That fellow will think 1 millivolt. Then we will ask him, what amplitude you have? That fellow will say, all our circuits, they work with 11 kV, 100 kV, right? Large amplitudes. Then you will ask him, what is the frequency? He'll say 50 hertz. Yes or no? So their frequencies are less, their amplitudes are more. Here our amplitudes are high, but our frequencies are less. But you cannot generate a high amplitude with high frequency. Here the turbine will shake. Yes or no? Can you have a 1 gigahertz sine wave with 11 kV? No, it's not possible, right? So it's like there's a limitation. If the frequency is large, there's a limit on the amplitude. If the amplitude is large, there's always a limit on the frequency, right? Okay, so find the maximum frequency. Find the maximum frequency for an undistorted output. Undistorted output. If the slew rate of op-amp is 5 volts per microsecond, the slew rate is 5 volts per microsecond. So my Vin is 2 sine omega t. So I'm having a sine wave where my frequency is varying from, say, omega varies from 0 to infinite, right? So I can give a small frequency or I can give even a large frequency, right? So now I want to calculate slew rate and I want to put a cutoff saying that more than this frequency, please don't send. Please don't give. If you give, the op-amp cannot, reproduce the same signal. There won't be any faithful reproduction of the signal. Definitely there will be distortion, right? So I want to put a limit on the frequency. Find the maximum frequency for an undistorted output if the slew rate is 5 volts per microsecond. So how are you going to solve? Please, slew rate is always calculated for the response, not for the input signal, but for the device response, for the circuit response. The response is V naught. Don't do dV in by dt. Slew rate is not dV in by dt. What is slew rate? dV naught by dt. The slew rate is always for the response, right? So now it's like just now I told you my son can write only 2 pages is maximum. So similarly, this op-amp maximum is like 5 pages of homework it will do, right? 5 pages, 5 volts per microsecond. Let's see if the signal output, what should be the maximum frequency to get this 5 volts per microsecond. Below that, if you give, happily it will work. If you give above that, definitely distortion will come, right? So let's see. What is slew rate formula? First, what is V naught? V naught is going to be 1 plus RF by R1 times of V. This is a non-inverting amplifier. It is 1 plus 3K by 1K times of 2 sine omega t. So 4 2s are 8. 8 sine omega t is your V naught. 8 sine omega t is your V naught. Am I right? Now what is slew rate? Slew rate is going to be dV naught by dt. So this is of what form? It is Vm sine omega t. What does Vm stand for? Vm stands for peak, 8. Omega is the frequency, angular frequency. What is dV naught by dt max? dV naught by dt max formula is omega into Vm. Omega into Vm. Omega into Vm. Omega into 8. Omega into 8. So therefore, slew rate is 5 volt per microsecond. 5 volt per micro. What is micro? Micro means 10 power minus 6. Micro, 10 power minus 6. 5 volt per microsecond equal to omega into 8. Omega into 8. What is omega value? It is going to 5 by 8 into 10 power minus 6. 5 by 8 into 10 power minus 6. So I want calculators. Tell me, calculators, what is this value? Omega. What is omega? 5 into 10 power minus 6 by 8 is omega. 5 into 10 power 6 by 8. Please give me in F also, F max. What is omega and what is F? What is F? Tiwari, right? So Tiwari says it's 99.47. Himanshu, 99.47. 99.47 is the frequency. Good, very good. Right, and 99.47 is the frequency. And what about omega value? Omega is going to be multiplication, right? So omega is some value that divided by 2 pi is going to be 99.47. 625 kiloradians per second. Okay, 625 kiloradians per second. Okay, so I'll go with frequency now. So I'll put a box here, right? Very good. Now you tell me if the frequency means the number of waves per second with an amplitude of how much? 2 volt. 2 volt amplitude. Frequency is 99.47 hertz. What happens if you give an input which is 150 hertz? 150 hertz. Then the slew rate for 150 hertz will be more, but the maximum capacity is only 5 volt per microsecond. Suppose if you give 150 hertz, the slew rate will be probably 6 volts per microsecond. But op-amp capacity is only 5 volt, right? Instead of 99.47, right? What if you give 50 hertz input? If your input is 50 hertz, maximum capacity is 99.4. If you give 50 hertz, happily it is going to what? Give the output with no distortion, right? So your F max, that means your omega n or F in should always be less than or equal to F max for no distortion. Your F in should always be less than or equal to F max for no distortion, right? And your F max is 99.5, 99.47, 99.47, right? Okay. Okay, so there's one more gate problem. The examiner says an op-amp has a slew rate of 1 volt per microsecond with a gain of 60 dB. What is 60 dB? 1000, right? The gain is 60 dB. This amplifier has to faithfully amplify signals from 0 to 20 kilohertz. Please tell me, for calculating slew rate, should I take F max or F min? F max or F minimum? F max, the biggest challenge is F max. You don't have to check for low frequencies. F max is important. If this amplifier has to faithfully amplify signals from 0 to 20 kilohertz, find the maximum input signal. Find the maximum input signal. So the examiner says that he has an amplifier whose gain is 60 dB. 60 dB. 60 dB means 1000. And its slew rate is 1 volt per microsecond. And he is giving an input here. This input will produce an output, and this input frequency is ranging from 0 to 20 kilohertz. 20 kilohertz. He is asking, find your V0 maximum. Find the maximum V0 max and Vin max. So he's asking, find the maximum input signal for no distortion. Find the maximum input signal for no distortion. So find V0 max, and we will find V0 max, and that V0 max divided by 1000 is going to be what you call for V0 max divided by 1000 is going to be V, right? An op-amp has a slew rate of 1 volt per microsecond with a gain of 60 dB. This amplifier has to faithfully amplify signals from 0 to 20K, find the maximum input signal for no distortion, right? Or I will give you 4 sine waves, right? Like I've given the homework example, right? So some sine waves can be reproduced at the output with no distortion. Some sine waves are reproduced with distortion. So I want you to check whether the signal input applied are distorted or not. The signal input applied are distorted or not. The gain of the amplifier, I'll give you 20 dB. What is 20 dB? 10. So this is my input. This is output. And slew rate, what shall we take? Slew rate. In the first problem, we took 5 volts. Second problem, 1 volt. Third problem, 10 volt per microsecond. 10 volt. Okay. So what is V in 1? You can take 0.5 sine 10 power 40. You have to check for this. It is 0.25 sine 10 power 70. It is 1.1 sine 3 into 10 power 60, right? It is 2.2 sine 10 power 5t. So I've given you few sine waves, but each of different amplitude and different frequency. So now with patience, we have to calculate omega into Vm, omega into Vm, omega into Vm for every sine wave. And that product should be less than 10 volt per microsecond, should be less than 10 volt per microsecond, right? Okay. Yeah. So tell me, an op amp has a slew rate of 1 volt per microsecond with a gain of 60 dB, right? So what is gain in dB? Gain in dB equal to 20 log gain. 20 log gain. So 60 dB is 20 log gain. 60 by 2. 60 by 2 is 3. So the gain is going to be 10 power 3, which is 1000. Which is 1000. So 60 dB means 1000, right? I'm having V in where the frequency varies from 0 to 20 kilohertz, right? So slew rate formula is 2 pi F max V max. V max. This is slew rate. What is the value of slew rate? It is 1 volt per microsecond. Microsecond is 2 pi. F max is 20k. 20k into V max. From here, what is V max? Tell me what is V max? V max. V max, it is 7.95 volt is V max. This is output. So if your output is 7.95, but your gain is 1000, gain is 1000, output V0 maximum is going to be 7.95 volt. What is your V in maximum? This is gain. Gain equal to output by input. Gain equal to output by input. So then what is input? Input is going to be output by gain. It is 7.95 by 1000. 1000. It is 7.95 millivolt. So you have to give an input which is 7.95 millivolt. And out of hastiness here, out of hastiness, instead of 20k, if you put 10k, what happens? Out of hastiness, instead of 20k, if you put 10k, then this 7.95, 7.95 means almost 8 volt, is going to become 16 volt. Is going to be, if I put 10k, is going to be 16 volt, and 16 volt at the output, I'm going to give an input that is 16 millivolt. What will happen? If my input is 16 millivolt, till my frequency is 10k, the slew rate of the op amp signal output, the slew rate of signal output will be less than the slew rate of op amp. Less than the slew rate of op amp. What happens if I give an input of 15 kilohertz? Because my maximum is calculated at 10. If I give 15, distortion will start. 16, distortion will start. 20 kilohertz, if you give full distortion will be there. Because the cutoff you calculated at only 10k. And accordingly, your input amplitude has increased. So naturally, the distortion will start after 10k. So slew rate of signal output should always be less than the slew rate of op amp. This is the condition for no distortion. No distortion. This is the condition for no distortion. So your Vin is going to be V0 max by gain. V0 max by gain. Okay, so check whether the signal input applied are distorted or not. What is the slew rate of op-amp? The slew rate is given as 10 volt per microsecond. So that means it is a 10 power 7 volts per second. The slew rate of op-amp or for the amplifier is 10 power 7 volts per second. Okay. Now, what is V01? V01 is going to be 10 times of V in 1. It is going to be 10 times of 0.5 sine 10 power 40. 0.5 sine 10 power 40. So how much is V01? It is going to be 5 sine 10 power 40. This is V0. And what is, this is of the form Vm sine omega t. Vm sine omega t. So what is the slew rate for the first signal? Slew rate 1. Slew rate 1 for the first signal is going to be the product of omega and Vm. Omega into Vm. It is 5 into 10 power 4 volts per second. 5 into 10 power 4 volts per second. So what is the maximum capacity of op-amp? 10 power 7. And what is the homework you have given him? The homework you have given him is to slew at what speed? 5 into 10 power 4. His maximum capacity is 10 power 7. Will he do this homework properly or not? Right? 5 into 10 power 4 is much lesser than his maximum capacity. So definitely he's going to do it. What is V02? It is 10 times of V into. It is going to be 10 times of V into is going to be 2.5 into 10 power 7. 2.5 sine 10 power 70. What is slew rate 2? Slew rate 2 is going to be omega Vm, which is 2.5 into 10 power 7 volts per second. Volts per second. Now tell me, what is his maximum capacity? His maximum capacity to do homework is 10 power 7, right? But now you are giving him a challenge to slew at 2.5 into 10 power 7. What he will say? Sorry, it's not possible. But if you say that, no, I will give a signal, you amplify. Then he will amplify, but shape of output will not be equal to the shape of input. Some, if you give sine wave, some trapezoidal, some random, some nonsense will come at the output. Now, if you ask him why you didn't give a sine wave, he said, my maximum capacity is only 10 power 7, but you gave me 2.5 into 10 power 7, right? 1 into 10 power 7 is my maximum capacity. 2.5 into 10 power 7 is not my capacity, right? So definitely this is going to be distorted. What is V03, by the way? V03 is going to be 10 times of V in 3, 10 V in 3, which is 11 sine 10 power 60. Now, what is slew rate for the third one? It is 1.1 into 10 power 7 volts per second. Oh, this is also gone because 1.1, his capacity is 1 into 10 power 7, right? 10 power 7, 1.1, slightly more. So this also will be distorted. What is V04? V04 is 10 times of V in 4. It is 22 sine 10 power 5t. So what is slew rate? 4. It is 2.2 into 10 power 6. Now what is the slew rate of amplifier? The slew rate of op-amp. The slew rate of op-amp is going to be 10 power 7. 10 power 7. Now slew rate of signal output should always be less than the slew rate of op-amp for no distortion, right? So therefore, who are distorted and who are not distorted? V01 is 5 into 10 power 4. So V01, V04 are not distorted. V02 and V03 are distorted. What do you mean by distortion? That means the shape of input, the shape of output does not match with the shape of the input signal. The shape of output does not match with the shape of the input signal. So 0.25, if you multiply by 10, it becomes 2.5. 0.25 if you multiply by 10, it is 2.5. 0.5 if you multiply by 10, it is 5. 1.1 if you multiply by 10, it's 11. And 2.2 if you multiply by 10, it's 22, right? Point 0.5 multiplied by 10 is 5. Okay. Okay. Now, what happens if op-amp has finite gain? Finite gain. If op-amp has finite gain, do not apply virtual ground. Do not apply virtual ground. So find V naught. V naught. If the open loop gain A is 10. A is 10. And of course, input resistance is infinite. Output resistance is 0. The op-amp gain is 10. So whenever op-amp gain is 10, do not apply what ground? Virtual ground. Virtual ground should be applied only when the gain is high. So do not apply virtual ground. Find V naught. Now find V naught. If A is 50, input resistance of the op-amp should be infinite, right? What if you have a worst op-amp? Input resistance 1K, output resistance 200 ohms. Input resistance 1K, output resistance 200 ohms. Now, for the first time, the output will also depend on the load, because if your output resistance is what you call 200 ohms finite, then it will also depend on the load. Okay, so let's solve it. When you cannot apply virtual ground, then you have to treat it as a general configuration of a difference amplifier, where V0 is A times of V1 minus V2. So this is the only thing you can do. The gain is 10, V1 is this voltage, and V2 we have to find, right? So it is going to be 10 times of 2 minus V2. It is 10 times of 2 minus V2. Am I right? Now, KCL. Entering current equal to leaving current, right? So 0 minus V2 by 1K is V2 minus V0 by 3K. So what is V0 by voltage or V2 by voltage division? V2 is going to be V0 into 1K by 3K plus 1K. It is going to be V0 by 4. So your V2 is V0 by 4. This is 2. Substitute 2 in 1. Your V0 is going to be 10 times of 2 minus V0 by 4. So this is going to give you V0. So first equation, KCL is same, but first equation is V0 is A times of V1 minus V2. A times of V1 minus V2. So what is V0 now? What is V0? What is V0? It should be less than 8. Otherwise 1 plus R2 by R1, it is 8 volt. Now this should be less than 8, right? How much is V0? $5.7. Okay, good. Your V0 is going to be 5.7. Otherwise, 1 plus R2 by R1 into 2, it should be 8. So when is it 8? Only when there is a virtual ground, but this is less, right? V0 is 5.7 volt, right? So similarly, V0 is A times of V1 minus V2. V1 is the voltage at non-inverting, V2 is the voltage at inverting. So it is 10 times of 0 minus V2, it is minus 10 V2. V0 is minus 10 V2. And now you have to apply KCL as usual. 1 minus V2 by 1K is V2 minus V0 by 10K. So it is 10 minus 10 V2 equal to V2 minus V0. V2 minus V0. So what is V0 from here? V0 is going to be 11 V2 minus 10. So from 1 and 2, you can get V0 and V2. So what is V0? Minus 10 V2, you just substitute here. V0 is minus 10 V2. Minus 10, that's 21. 21, 10 by 21. 110. How much is V0? How much is V0? Minus 4.76. So this is going to be by 10. 0.476. 0.476 into 10, it is going to be this, right? So if you multiply by 10, you're going to get the output, because VD is going to be V1 minus V2 is minus 0.476. Your V0 is A times of VD. Now the difference VD is 0 if the amplifier is ideal, but now the amplifier is non-ideal, so definitely. So your V2 is going to be plus 0.476, and V1 minus V2, 0 minus of this value is this. So this multiplied by 10, right? 0.476 and minus 4.76. Okay, good. So let's draw the equivalent of an op-amp. This I have given you long back. Op-amp is basically a VCVS, all right? This is RID, A times of VD and R0. And I've given you a conclusion that IOP, the op-amp current, is going to be 0. IOP is 0 only when RID is infinite. Op-amp draws no current only when the input resistance is infinite. And V0 is AVD. V0 is AVD only when V0 is going to be AVD only when R0 is 0. R0 is 0. And V plus equal to V minus in negative feedback. In negative feedback, or V1 equal to V2 in negative feedback only when A is infinite. Only when A is infinite. Now we have violated every situation here. So the examiner cannot think of anything worse than this. Your input resistance is finite, output resistance is finite, the gain is also finite. So in such an occasion, how will you solve? Okay. What is RID? 1K 200. This is 1K. R0 is 200 ohms. Gain is 50. 50 times of, what is input? 2 volts, huh? 2 volts. One K, 3K. Load is 2K. It is 50 times of this. I'm calling it V2. V1 is already 2. V1 minus V2. 50 times of 2 minus V2. Because your V1 is 2. Your V1 is 2, right? 50 times of 2 minus V2. So now you have two unknown nodes again. Same two equations you will get. There is no difference. In the previous question, there are two equations. Here also two equations. So give me KCL. Sum of currents that leave a junction is 0. V2 minus 0 by 1K plus V2 minus 2 by 1K. V1 is 2 plus V2 minus V0 by 3K equal to 0. Now again, sum of currents that leave a junction is 0. V naught minus 50 times of 2 minus V2 by 200 plus V naught by 2K plus V naught minus V2 by 3K equal to 0. So from 1 and 2, you can get V naught and V2. From 1 and 2, you can get V naught and V2. Right? So this is V1, this is V2, this is VD. Am I right? Or if you want, you can draw here itself, right? So here itself you can draw like this. That's better. Yes or no? Why again separate page? Huh? Here directly you can draw like this. So here you can draw. This is V1, this is V2. Here you have R0, this is AVD, or A times of V1 minus V2. And this is your RID. And here one KCL here and the other KCL here. That's it, right? Okay, so you can find that. It's not a big thing. So here you have VD, all right? This is VD, V1 minus V2. So first equation has V2 and V0. Second equation has V2 and V0. So there are only two unknowns. So if you solve it, you can get V2 and V0. Okay. The next non-ideality is CMRR. It is CMRR. What is CMRR? Common mode rejection ratio. What is CMRR? CMRR is common mode rejection ratio. Here, frequency I've changed. In the comment section I'm getting frequency, I made it mistake. What is the mistake I've made here? 10 power 4 is there. 10, acha, 3 into 10 power 6. I didn't took 3 into 10 power 6. Okay. Good catch. Good catch. I stand corrected. 3 into 10 power 6 I didn't took, right? I took only 10 power 6 here. I didn't observe the 3 into 10 power 6. Very good. Very good. Very good. Okay. CMRR. What is CMRR? It is the ratio of differential gain to the common mode gain. So CMRR is given as AD by AC or ACM. CMRR in dB, it is given as 20 log AD by ACM. CMRR in dB is given as 20 log AD by ACM. log AD by ACM. So who is the actual gain for an op amp and who is the error here, right? Who is the error? If you have two inputs V1 and V2, what is V0? V0 is A times of V1 minus V2. Am I right? V0 is A times of V1 minus V2. This A is AD. V1 minus V2 is VD. What is A? A is the differential gain. V1 minus V2 is the difference. AD, VD. So this is only an ideal situation. Ideal case. So if you think V0 is A times of V1 minus V2, it is only an ideal situation. But in a practical circuit, it is going to be AD, VD plus ACM, VCM. ACM, VCM. This is the error. This is the error. So this is a practical op amp. Now you might say, who is this common mode signal here? Noise. Noise is a common mode devil. How good a differential amplifier or an op amp can associate itself close to different signals and how it can kick off the common mode noise. Because we know when I apply the signal is going to be the differential amplifier will cut that signal into two parts. We have seen what is there. You might give V1 equal to 2 sin t, V2 equal to 0. If V1 is 2 sin t, V2 is 0, internally, what a differential amplifier will do? The 2 sin t is going to cut into two parts. The first differential amplifier is going to take 1 sin t. The other differential amplifier is going to take minus 1 sin t. So now you know the main purpose of a differential amplifier is not to amplify the difference. It can even, you can give a simple common emitter amplifier, give a signal, whatever the gain you get in common emitter, the same gain you are going to get in differential amplifier also. But it is not to amplify the difference, but it is to reject the common mode signal. The common mode signal will have common perturbations, the common variations. Whenever there's a common variation, when you take the difference after amplification, there is going to be a rejection, right? Rejection. That is why it is called common mode rejection ratio. Why it is not called common mode elimination ratio? Because you cannot eliminate it completely. You can only reject. When you reject it, some amount of noise is also being amplified. A little, right? How much it is being amplified is given by CMRR. Here, AD/VD plus ACM VCM. Now, what is the percentage error here? We know that it is AD/VD, but who is this extra factor, extra masala here? ACM VCM divided by AD/VD. Am I right? But actually should be it is AD/VD. Now it is ACM VCM by AD/VD is that extra percentage error. So it is AD/VD into 1 plus what is CMRR in dB? CMRR in dB is going to be 20 log AD by ACM. So what is AD by ACM here? AD by ACM is going to be 10 power CMRR in dB by 20. So if I write VCM by VD here, what is ACM by AD? What is ACM by AD? It is going to be 1 by 10 power CMRR in dB by 20. 1 by 10 power CMRR in dB by 20. So this is going to be the percentage error. Now you tell me how much of CMRR is accepted. Suppose student will ask, sir, how much CMRR should I buy? If you buy a 741 op amp, CMRR will be 100 dB. So what is 100 by 20? What is 100 by 20? 100 by 20 is 10 power 5. So if your VCM and VD are even equal, right? The different signal and the common signal, 1 by 10 power 5. That means if you are expecting a magnitude of 1, then 1 by 10 power 5 means 0.00001 will be the error. Will be the error. Are you getting? If you ask me, 60 dB and above is a good choice, right? Because 60, what is 10 power 60? CMRR 60 by 20 is going to be 10 power 3. The error is close to 0.1%. So if you want the error close to 0.1%, 60 dB and above is always a good choice. But 741 has got 100 dB, so it is like bumper Diwali offer. Are you getting? So if you use a CMRR of 100 and above, it is excellent, right? But 60 and above should always be a good choice, right? So the percentage error in terms of CMRR I have given here. So if the examiner asks what is the percentage error, you should say VCM by VD into 1 by 10 power CMRR in dB by 20. Are you getting? Now, what is a simple way of calculating CMRR? A simple method or a simple formula, we can say formula to calculate CMRR. What is a simple formula? I'll just derive the formula, but finally you remember the formula, right? You just don't remember the whole derivation, just remember the formula, just apply the formula, you will get it, right? Now tell me, when I started the differential amplifier, I told you that if you give a signal to a single line, what is the problem if you give a signal to a single line? V1 is there. If you give a signal to a single line, V, then there will be some noise N. At the receiver end, you are going to get signal plus noise, right? Then I told you that we will take two lines, and if you give V here, you give minus V here. If you give minus V and let noise be a common mode devil, when you add it, what will be the difference? The difference is going to be V minus of my 2V. 20 log 2. 20 log 2 is 6 dB gain. You get a gain of 6 dB, 2 times of V, but the common noise is going to get cancelled. Are you getting? In fact, if you ask me, this technique they have applied in telephone lines. In telephone lines, initially, they used to send voice signal over a single line. When they used to send voice signal over a single line, you know that noise is always there in the channel. So at the receiver end, they used to get signal and noise. Then they felt, no, we want to reject this common noise. And noise is inevitable. Somehow you are going to get noise. So they started sending voice signal over two lines this time. But when they sent over two lines, they have flipped the signal at the other line by 180 degrees phase shift. If you give V here, they used to give minus V. At final receiver end, you are going to get V minus of minus V, 2V, and the noise is going to get cancelled. So let me apply the same trick here. What I'm trying to say is, if you are getting VD here, it is understood that this line has VD by 2, this line has minus VD by 2. Am I right? Because when you have VD by 2 and minus VD by 2, then the difference is going to be VD. And noise is a common signal, VCM and a VCM. So any two signals by nature can be represented as having a differential component and a common mode component. What happens even if there is noise? Don't worry. When you take difference, what will happen? this VD by 2 minus of minus VD by 2 is VD. You'll get only the difference, and your VCM is going to get cancelled. VCM is going to get cancelled. So this is something we know that is happening practically. This is a practical situation, right? Practical situation. Now, see, I'm not very good at mathematics, but still I enjoy, this part of math. There's simple mathematics. Mathematics is very simple. And if it can speak a lot, I really appreciate it. So how to bring this practical situation with simple mathematics? A simple mathematical equation should bring this practical situation, right? See here, the mathematics which can bring this practical situation is this. V1, can I write V1 as V1 by 2 plus V2 by 2 plus V1 by 2 minus V2 by 2? Now you might say, what is this? V1 by 2, V2 by 2, V1 by 2 minus V2 by 2, that is V1, however, okay. But V1 plus V2 by 2 is the common signal. V1 minus V2 by 2 is VD by 2. So I really love this mathematics because a signal, a general signal, I'm able to represent as if it is having a common mode component and a differential component. So similarly, what is V2? V2 by 2 plus V1 by 2 plus V2 by 2 minus V1 by 2. So this is going to be VCM, common signal, minus VD by 2, minus VD by 2. So any two signals can be the summation of differential signal plus common signal. Are you getting? This is something, if I write this, what people will say, this is a practical situation that is happening. You will have a noise as well as a signal. Are you getting? On one line. On the other line, the same signal, but the same signal with 180 degrees phase shift plus the same common noise. When you take the difference, the common noise is going to get cancelled. You're going to get only the signal. Okay. Then where is CMRR here in this representation? CMRR in this representation is, I will apply superposition theorem and give you. See here, V0. What is VD here? VD is V1 minus V2. Just tell me, instead of subtracting, if I add, what will I get? Suppose two signals are there, V1 and V2. I'm going to add them. What will I get? If differential amplifier, instead of differential amplifier, if you have a summer, what will happen? VD by 2 minus VD by 2 will cancel. You will get 2 VCM. So V1 plus V2 is 2 VCM. That means VCM is going to be V1 plus V2 by 2. Am I right? VCM is going to be V1 plus V2 by 2. So if you add both, it's always going to be 2 times of VCM. Okay. So now I am able to represent two signals, V1 and V2, as the summation of differential component plus common component, right? So it has got a VD by 2 and it has got a VCM. And V2 has got a minus VD by 2 and it has got a VCM. This is just a model, okay? So now, how will I get CMRR from this equation? Superposition. What is superposition here? This is V1 and this is V2. Tell me, superposition. Can I say from the lower diagram, V0 is A1 V1 plus A2 V2? A1 V1 plus A2 V2. From the upper diagram, I can say that V0 is AD VD plus ACM VCM. ACM VCM. So what do you mean by this? What do you mean by this? There are 4 components here. 4 components. VCM, VD by 2 minus VD by 2 and op amp. So just an analogy, take it light-heartedly. Suppose I want to make a fruit juice. I want to make a fruit juice. This is a blender. This is a blender. Now how to make a fruit juice? To make a fruit juice, tell me 4 things. 4 things that are needed to make, right? One is fruit. Then the other one is, how do you make a fruit juice? Ice. Then milk, okay. Milk and sugar. Sugar, right? Now, how do you make a fruit juice now? To make a fruit juice, I will use fruit and ice first. Fruit and ice, A1, V1. A1 V1 is fruit and ice and sugar and milk, right? Fruit and ice, sugar and milk. What is ADVD? What is ADVD? This time I'm going to use ice and milk now, ice and milk, right? VD, and then ACM, VCM, fruit and sugar, right? But here A1, V1, A1 is this complete V1 is fruit plus ice, and A2, V2 is milk plus sugar, right? So fruit and ice, milk and sugar is same as ice and milk and fruit and sugar, right? So if they're same, if superposition holds good, then VD is V1 minus V2, and VCM is going to be V1 plus V2 by 2. This is A1 V1 plus A2 V2. Now if you solve this here, you get what is AD here? AD is V1. A1 is going to be AD plus ACM by 2, and A2 is going to be ACM by 2 and minus AD. And what is finally, what is AD? AD is A1 minus A2 by 2, and ACM is going to be A1 plus A2. This is CMRR formula. See how simple. AD is A1 minus A2 by 2. ACM is A1 minus A2. CMRR formula is going to be A1 minus A2 by 2 times of A1 plus A2. So whenever you find any difference amplifier, you want to calculate CMRR, you can do this, right? Forget about AD, ACM and all that. A1 minus A2 by 2 times of A1 plus A2, where A1 is going to be V0 by V1 when V2 is 0. Superposition, right? V0 is A1 V1 plus A2 V2. V0 by V1 plus V2 is 0, and A2 is going to be V0 by V2 when V1 is 0. So let us use this formula, right? Very, very simple formula. We can use this formula for calculating CMRR. So numerator A1 minus A2 by 2 is going to be AD. Denominator A1 plus A2 is going to be ACM. Then A1 minus A2 by 2 times of A1 plus A2 is going to be CMRR.
Hello, sir.
Hello, sir.
Yeah.
Sir, why we use the transistor in a Zener circuit?
Why you are using transistor in Zener circuit? Acha, already doubts have started. Still 5 minutes is
Yes,
there.
sir. Started, sir.
Already started.
Started, sir. Yes, sir.
5 minutes is there already. Okay. Yeah, tell me. Why transistor is used in Zener circuit? What do you mean by that? That is an integrated circuit, no? You have to use transistors and MOSFETs if you want to make an IC.
Sir, the Zener is not operating at a high voltage. That's why.
What is not operating at high voltage?
Sir, Zener.
Yesterday, you want to increase the current range, then we have to use a power transistor there. Yes, you are right.
Okay, sir. Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, in practical integrator, you discussed that at high frequencies, gain will be very low, no, sir?
It will be low, but it will still give you some integration there.
There is no distortion, sir, in that case. Then distortion will be not there, no, sir, in that case.
The distorted output is the integrated output. What is distortion? When the shape of input and shape of output are not same, no?
Yes, sir.
I am giving sine, you are getting cos.
Yes,
A
sir.
person who has designed low pass filter, he might think it is distortion. But a guy who's designing an integrator, he'll say thank you.
Okay, sir.
Are you
Sir,
getting?
page number. Yes, sir. Getting, sir. Sir,
Yeah.
page number 26, sir.
26.
Yes.
Uh,
Okay, sir. Okay, sir. Okay. Sir, another doubt is, sir. We used LM7805. No voltage regulator, no, sir, in practical.
yeah, yeah.
Sir, in that case, it is only output is only 5 volts, no, sir.
Yes, yes,
Constant.
yes.
Means that then in that internal circuit there is no op amp, sir.
Yeah, inside there will be op amp. That is why maximum you can drive it up to 1 ampere. Op amp means op amp will not be there. Differential amplifier will be there.
Yes, sir. But we can vary the load, no, sir. In this case, up to 5 volts we can use any load.
You can use, but current less than 5 ohms, you should not connect load. 5 volt by 5 ohm is 1 ampere. No, that is the
1
maximum
ampere.
current it can handle.
Okay, sir.
If
Got
you
it.
put 0.5 ohm load, you want to drive a robot, then
Yes,
5
sir.
by 0.5, 10 amperes of current means smoke will come from IC.
Okay, sir. Got understood, sir. Sir,
Yeah,
32F, sir. One last doubt, sir. 32F.
Sir, tomorrow class timing, sir.
32.
Yes, sir.
Yeah.
32F. Sir, this 2 pi into F max, V max, it is applicable only for sinusoidal input, sir.
Yes, yes, yes. This is slew rate for sine. If they
Sir,
give
but in
triangular means you calculate slope. Y2 minus Y1 by X2 minus X1.
sir, in this question they didn't mention, no, sir. It is sinusoidal or not.
0 to 20 kilohertz. Yes, these are sinusoidal input. Faithfully amplify, you can write here sinusoidal signals.
Okay, sir. Means it is only applicable for sinusoidal.
Yes, yes, you are right.
Okay, sir. In any other signal, we have to differentiate and we have to find the slope, sir.
Absolutely correct.
Okay, sir. Got it.
Very good.
Okay,
Sir, hello,
Thank
sir.
Yes.
Sir, I want to ask, class over or you will teach?
Class is over, no? Already doubt session is started.
Sir, that's why I called. Okay, sir, thank you.
Yeah, yeah, yeah.
Hello, sir.
Yes.
Sir, I'm having doubt in yesterday's class, sir.
Tell me.
Sir, in 17F, sir.
ज्यादा नहीं देर में बात करें क्लास चल रही है ठीक है
17F.
Yes, sir.
Uh,
Sir, actually, in yesterday's class, 17F, sir, we have connected one diode and, sir, can you please open that, sir?
Birthday that
yeah. Tell me.
17F.
This is today's class, no? No.
Yesterday's. Sir, not the, sir, yesterday's class, sir.
This is not yesterday.
Yes, sir. Yes. Sir. Sir, actually, in first case, for diode to be on, we need only 0.7 volts to be
Yes, yes.
given.
Yeah, right.
Then Vin is greater than 2.7 you took, sir.
Anode, this is diode, no? Cathode, if it is connected to ground, then 0.7. It is already 2. This one is 2 volts with respect to ground. And it needs 0.7 here. That means this should be greater than 2.7. No?
Okay, sir. Okay, sir. Sir, and sir, in second case, how we are taking, sir?
You have to, that's what I told you, no? Positive cycle, you have to put arrow like this and move the pen like this.
Okay, sir.
If it flows from anode to cathode, it is on.
Yes, sir.
Now, once this is on, this cannot be on. Negative cycle, you have to put arrow like this and move the pen like this. Can it go like this? No. It will go like this, no? This is negative cycle. Current is flowing from anode to cathode, 0.7 volts.
Okay, okay. Zener required less current to activate that, sir.
0.7 volts is enough for
Yes,
Zener
sir.
to get on in forward bias.
Yes, sir.
Uh,
Sir, and 24, sir. Sir, actually, that left side diagram I not understood, sir.
you draw, instead of diagram, you draw straight line, that is enough, no?
Okay, this is only for reference.
Reference for, there will always be a non-zero voltage. For every current, there is a non-zero voltage. 2 volt, 3 volt, 4 volt, like that. 5 volt. But once after getting 5, the output will always be 5.
Okay, okay, sir.
So this just tells you that you can get 0 volt, 1 volt, 2 volt, 3 volt, 4 volt, any voltage across the Zener if it is non-linear. If it is
Okay.
piecewise linear, like this, then it will be 5 or 0, that's all.
Yes, sir. Like binary.
Yeah. Here 0 or 5.
Okay, okay, sir. Sir, and the last note, sir, 29, sir.
Yeah.
Sir, this I'm not getting, sir. How the problem? I didn't understand the problem, sir.
No, you have to take two currents, that's all. IZ 1 milliampere, 60 milli and solve. You first take 1 milli here, IZ. This is
Okay.
already 10 milli, no? 10 by
Yes.
1K.
Yes, sir.
This is 10. 10 by 1K is 10 milli.
10 milli.
This is 1 milli. Kirchhoff's law says that 10 plus 1 is 11 milli.
Okay, sir.
So 11 into 300 plus 10. That means 13.3 you have to give at input.
Okay, okay.
Next case, this is 60 milli. 60 plus 10, 70. 70 will flow. 7 3s are 21. 21 plus 10 in this loop, 31 volt you can give. So the range is between 13.3 31.
30. Okay. And knee current should be less for the Zener to on, right, sir?
That is the minimum current you have to give to for the Zener to be on. Less than that, if you give, he will not give 10. But if you give 2 milli, 3 milli, 5 milli, 8 milli, 10 milli, any current, it is going to get on. Minimum is 1 milli.
1 milli.
It is like the qualifying marks for gate.
Okay.
If you get more also, it is okay, right?
Okay, sir.
Minimum is that. That is called the knee current. Minimum current.
Okay.
Hmm.
Okay, sir. Thank you, sir.
Yeah.
Hello.
Yes.
Sir, I have a doubt in the Darlington pair, the transconductance of Darlington pair. Actually, sir, there is a question in previous year in which the answer is 0.5 GM2.
That is
We have
wrong.
calculated the
That is,
GM2. That is wrong, sir.
That is what I said is correct.
Sir,
Everything is wrong.
Yeah. Okay, sir. Actually, in 2 books I got that answer. That's why I was asking. And same question I posted in Telegram.
Yeah. That is wrong. Absolutely wrong.
Okay, sir. Actually, sir, what they have did, they have short circuited the collector terminals of both the
See, the
transistors.
nonsense what they are doing is first transistor is a common collector amplifier. Emitter
Yes, sir,
follows.
yes. Yeah.
Output and emitter should follow input.
Yes,
So
sir, yes.
that VB they are taking 0.7 like that.
Yeah,
VB plus
sir.
VB, 2 VB they are doing. First
Yes,
of all,
sir, yes.
transconductance is a AC parameter, not DC. How
Yeah.
they can add 2 DC voltage, 0.7, 2 VB they are taking. Are you getting?
Okay,
So
sir.
I don't know. So I have not given that solution. I will change it. No problem. I will ask them
Okay,
to
sir.
change.
Thank you.
Yeah.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Sir, I have a doubt in today's class.
Yeah. Tell me.
Once you open,
Huh?
once you open, sir, today. 42. Sir, can you explain this again, sir? We not.
See, this V1 equal to VCM plus VD by 2, no? I'm just drawing it with a diagram, that's all. Directly we can prove. I'm drawing with a diagram and I'm showing you different components. What is superposition theorem? Superposition theorem says that you can even take two sources at a time. It is not like you have 4 sources are there, one you have to take. Here two we have taken. V1 separately we have taken. V2 separately we have taken. V1 means 2 sources. Are you getting? This is V1 with respect to ground. That means this source plus this source is V1. This source plus this source is V2. Next to what we are doing, these two we are taking. These two we are taking. VCM once, VD once. Final output should be same. Whether you do A1 V1 plus A2 V2 or you do AD VD plus ACM VCM, it is same.
Actually, V not equal to V1 minus V2, no, sir.
V naught equal to A times of V. Superposition theorem. A1 V1 plus A2 V2.
Y plus, sir. Actually, minus.
Huh?
Actually, minus.
No. Superposition theorem, linearity property. You don't think there is an op-amp. You think it is a difference amplifier with 2 inputs.
Okay, sir. Got it, sir. Difference.
You think it is an instrumentation amplifier. CMRR is not for op-amp only, no? You have an instrumentation amplifier with 2 inputs. Or you have a difference amplifier with 2 inputs. Then how you will do? You will keep one source with other source, you will short and find, no?
Yes, sir. Yes, sir. Okay, sir.
Hello, sir.
Yes.
Sir, what a CMRR exactly is? Like you said, slew rate means the rate at which
Slew rate is only speed.
Yes.
CMRR is
rejecting
rejecting common signals. Ability of a op-amp or difference amplifier to associate itself with differential signals and kick off the common mode noise.
Sir, what is that common mode noise?
It's corruption. Every signal is going to get corrupted with some noise. In a differential amplifier, the variation of temperature is noise. Noise means any unwanted signal. That corruption we have to remove.
Okay,
And we have to get our signal. Only our signal should be amplified, not the corruption.
Then why the word common mode is used?
Because it's common for both inputs, no? See, suppose an IC is there. In this IC, 2 pins are there. This pin will not be in Hyderabad and this pin will not be in Delhi. Those 2 pins will be very, very close by. And it is expected that whatever temperature is there at this, the same temperature variations will be at that pin also. So all transistors, they are going to experience same temperature changes, no? IC where it will be some on circuit board. But whether that board you are using it in an aircraft or in your house, the temperature in all the ICs are going to have same variation or transistors. Then such signals are called common signal, common variations. Those common variation we have to reject. The best way to reject is by a differential amplifier. We will welcome it. We will welcome the common mode signal. And when you take difference, the common variations will get cancelled. That is the logic.
Okay, sir. And sir, in 16.
Yeah.
Sir, that input offset voltage.
If there is RF parallel RN, we have already calculated here, no?
Sir,
If there is RF parallel RN, RF into IOS.
No, sir, I guess I missed the page. The 2 graphs you have drawn there, ideal op-amp and practical op-amp.
That is VOS. This one, no?
Yes, sir. I have not understood the graph of practical op-amp.
See, the practical op-amp has got some shift here from 0. If it is shifted to -2 millivolt, then such op-amps, when you want, if at all you want to model it, if you put like this, suppose this diagram if you give, and you say that this is my practical op amp, then the answer given by this diagram will never match with the practical op amp. For this op amp, this is the change you have to make in the model. What is the change? If there is a -2 millivolt shift, you have to put +2 millivolt here. Then your operating point is going to be same. How? If you give +2 millivolt here, if you give already plus is there, no? If you give -2 millivolt, what is -2 millivolt plus 2 millivolt? 0. Yes or no?
Yes.
So when I give a voltage of -2 millivolt, if I give a voltage, see, I will not show you what is there inside. Inside there is a 2 millivolt inside. I'll put this in a box. Now I am going to give here, I want to check my graph. I want to give -2 millivolt. Then what is your output? How will you do? You'll do V0 equal to A times of VD, no? But
Yes, sir.
-2 millivolt, already inside 2 millivolt is there. -2 millivolt plus 2 millivolt is what? 0. Your output is 0. Then you'll say, see, I got this point.
Okay, sir.
Then you'll say,
And-
okay, what if I give -3 millivolt? Will you give -VSAT? Okay. -3 millivolt I'll give. -3 millivolt plus 2 millivolt is -1 millivolt. -1 millivolt into 10 power 6 minus VSAT. See, I got this.
Yes, sir, got it.
If you give -1 millivolt, you give -1 millivolt. Already 2 is there. 2 minus 1 is 1 millivolt. 1
Yes,
millivolt
yes,
into 10 power 6 plus VSAT. See, I got plus VSAT.
Yes, sir.
So
Thank
for
you
a
so much.
practical op amp, this is the model. This is only the model.
Okay, sir.
So you can treat it like this. Otherwise, if you take an ideal op amp, for that ideal you put a VOS here, then this becomes a practical op amp. Are you getting?
Yes, sir.
Yeah.
Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, good evening, sir.
Yeah, good evening. Tell me.
Sir, if they didn't mention about gain means we need to take infinite, no, sir?
Yes.
Sir, virtual ground concept is applicable only for infinite gain, sir, or high gain?
For high gain or infinite gain. Gain will, in exam, there are only two types of gains. One is infinite gain, another is 10 or 15, like that.
Okay, sir. Can you go to 7F, sir? Sir, you told about moderate gain, sir, and the op amp is behave like an ideal op amp. Sir, it should be high gain, sir.
See, if op amp has very high gain, means all offset problems will come, no?
Yes, sir.
Your VOS will be multiplied by that, it will saturate. Gain should be okay. See, there is no point in having still more gain. As long as you operate at moderate gain. Moderate gain in op amp means in lakhs.
Okay, sir.
Okay.
Sir, can you go to
Hello?
32
Yeah.
F, sir? 32
30?
Hello.
32 F, sir.
Hello. Hello.
Yes. Yeah.
Sir, here the
Hello.
slew rate of op amp is 1 volt, sir. Sir, what is the value of slew rate of signal output, sir?
You have to calculate, no?
Oh, no,
Slew rate of
unmute
signal
Radhika,
output should
Radhika.
always be less than the slew rate of op amp.
Unmute करना दिखा मैं
Okay, sir.
unmute.
If it is 10K, it is going to be 0.5 volt per microsecond.
Yes, sir.
If it is 5K, it is going to be 0.25 volt per microsecond. If it is 20K, it is going to be 1 volt per microsecond.
In this question, they didn't mention about we need to find the slew rate of signal output, no, sir?
No. We have to find peak amplitude. First problem is for signal output. Second
Okay,
problem, this is for peak amplitude. Third problem is many signals with many amplitudes with many frequency.
Okay, sir.
Hello.
Thank you, sir.
Okay. Yeah.
Hello. Hello.
Yeah.
Hello, sir.
Yes.
My name is Nadim. I didn't write the slew rate topic. Page number 35. Hello.
Yes.
Slew rate topic. 27 or hello.
Yeah. One by one. Wait. He's asking me about slew rate. No. Tell me. What is that you have not understood in slew rate?
I didn't get about didn't understood about the slew rate, sir. Today is my first class. That's why.
Today is your first class. Slewing means speed. So who is controlling speed here? The capacitors, the junction capacitors in a transistor.
Okay.
Every transistor will have junction capacitors. Because of it, capacitor will not allow sudden changes, but it cannot avoid the change. So output in a flash, suddenly output cannot go. If input changes, output in a flash cannot change. It takes some time to change. That time is called slew rate.
Okay. And
Now, the question is, whenever I'm talking over a microphone, you are able to listen my voice instantly, no?
yes, sir.
How you are able to listen my voice instantly when I'm talking here? Because the time scale of my input signal is much larger than the propagation delay of the circuit. Propagation delay is calculated by resistors and capacitors. Time is calculated by the period T, tau. Tau is R and C. My signal will also have some period, no?
Yes.
If my signal period is large and the device RC is small, so device RC speed is high, signal speed is slow, then no problem. You will have distortionless transmission.
Yes.
But if your signal input frequency is very, very large, tuck, 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 it is changing. But the RC value is small, then definitely you will get output distorted, no?
Yes, buffering sounds and some burbering.
Yeah, you will have distortion. So how to avoid that? There is a limit you have to put. That limit is this omega into Vm, amplitude into frequency. That product should always be less than the slew rate of the op amp.
Okay. Sir, once show me the definition of that, sir. I didn't write that one. Slew rate definition one.
Slew rate definition, it is a maximum rate of change of output voltage.
Hello.
Yes.
Yeah, good evening, sir.
Yeah.
So you said in a ideal integrator, capacitor charges to infinite at time t equal to infinite.
Tell me.
Yeah, at t in ideal integrator, you said that t equal to infinite, voltage will tend to infinite, no, sir.
And see, capacitor is charging. Slowly what it will do? 1 volt, 2 volt, 3 volt, 4 volt, it will keep on charging now.
Yeah, but the voltage is VOS only, sir. No, sir.
It is 1 plus RF by R1 times of VOS, no?
Yes, sir.
Before after connecting resistor or before resistor?
After connecting.
After connecting resistor, you have stopped it. 1 plus RF by R1 times of VOS only it will charge output.
Business account.
Because resistor is there, no?
Yeah, okay.
In steady state, you can treat capacitor as an open switch. Then maximum it will charge to 1 point. Suppose if your RF is 9K, R1 is 1K, VOS is 0.1 volt. That means 1 millivolt it will charge. What is there?
Okay.
Are you getting?
Yeah.
Yeah. Next. Anybody else?
Hello,
okay
sir.
then.
24F, sir. 92F. Hello, sir.
Yes.
Sir, can you open 22F? Sir, for this, can we apply?
कमांडिंग से बात करें उसे याद रख ले कैसा कमांडिंग
Sir, can we apply non-inverting terminal?
The non-inverting 10K and 1K are in parallel, no?
No, sir. When we are taking in the question, not during calculation of error. Normally, if we are not doing superposition.
No, without superposition also first you have to calculate, no? R2 by R1 into V1 minus V2. Hello?
Yes, sir.
What is your doubt? You want me to apply virtual ground here and calculate?
No, sir. Can we apply voltage divider at non-inverting terminal or not?
Yeah, you have to apply 3 into 10K by 11K is this voltage. That voltage will be here. Apply entering current, leaving current. You will get it.
But there is a leakage current now, sir. You said we should not apply voltage divider when we have leakage current outside.
Where outside? This IP and IN, huh?
Yes, sir.
You take IP and IN and apply. Here there is IP, no?
Yes, sir.
Here there is IN. Entering current equal to leaving, you apply KCL.
But voltage divider we cannot apply, right?
No, because current is flowing, no? You are right.
Okay, sir.
Yeah, good.
Hello, good evening, sir.
Yeah.
Sir, I did not have a doubt. I waited for this, sir. Like today you were teaching, it's your means you are the authority. You will unmute means when your class will be over, then you will give chance for doubt. No, sir, you will tell when the doubt session will start.
Yes.
Then random that guy, sir, means like I just wanted to tell means like if I get this option of how to means from your side you can do this unmute part, then I will send you, sir. Means like you had 5 minutes or either 2 minutes was also left, but when you will say then only doubt session should start. No, anyone random would start speaking, then it's wrong, sir.
Oh, thank you very much. Yeah, I think you are right.
So that only, sir, you were with the flow of CMRR and suddenly someone asked out.
The fact is I wanted to solve one problem in CMRR in 2 minutes.
Yes,
that's
sir,
okay. Then again tomorrow we have to use that formula A1 minus A2 by 2 times of A1 plus A.
No, sir, then can I send you this settings means like from your side you can unmute, sir, means like.
Yeah, I think now I can unmute. I think there is a setting here.
Yes, sir. And sir, one more thing was like for Narasimha sir's class and Vivek sir's class, this raise hand option was only not there. Means like if it is disabled, then no one would be able to raise hand. When the doubt session starts, then only one by one they will raise hand and we'll get chances.
No, the raising hand from starting they are raising, no?
That is only the issue, no, sir. If people are raising, then they get an unmute option. Then if the person unmutes, then he does not mute, then the background sound also comes from that side.
Yes. You are right.
So that only I was telling, sir. Means in the beginning of the class, if you disable this option and when doubt session starts, then you start this, enable this, then it would.
So how I can wait? Disable participants annotation is there. That one, huh?
Sir, I don't have idea. I will send you a screenshot if I get, means like later I will send you on WhatsApp.
Yeah. Please go ahead.
Okay, sir. Okay. This one.
Yeah.
Thank you, sir. Thank you.
Yeah. Indirectly बोला. मैं बोलेंगे लिंक आइए.
Hello, sir.
Yes.
Good evening, sir.
Yeah. Tell me. Good evening.
Hello. Sir, there is an in which LNC were given and asked to find op-amp gain.
What is given?
Frequency of oscillation. Sir,
What is given?
LNC at non-inverting side with R connected to output and RF and R1 connected to inverting side.
That is oscillator problem. I will do in class.
And we are to. Okay, sir.
That is oscillator problem. I will do in class. It is simple only. We have to calculate the loop gain and equate it to 1.
Sir, can we take LS short circuit and CS open or something like that?
No, for for gain you can do, but for frequency F equal to 1 by 2 pi root LC, no? Standard formula.
Yes, sir.
Hello? If it is RC, you can do 1 by 2 pi tau. Tau is RC or L by R or root LC. You can use those formulas.
Good evening, sir.
Yeah.
సార్ ఈ డిఫరెన్షియల్ యాంప్లిఫైర్ ఉంది కదా సార్, మనకి అటు సైడ్ బీజేటీస్ ఉంటాయి. ఈ డిఫరెంట్ ఒక సైడ్ మనకి ఆర్సీ ఉంది, ఇంకొక సైడ్ ఆర్సీ లేకపోయినా కానీ మనకు అప్పుడు ఈ రెండు సిమెట్రికల్ స్ట్రక్చర్ అయినా సార్?
సిమెట్రీ అంటే మీకు అవుట్పుట్ వస్తుంది, ఒక దాంట్లో అవుట్పుట్ ఉండదు. ఆర్సీ లేకపోతే, రెసిస్టర్ లేకపోతే కరెంట్ ఉంటది, వోల్టేజ్ ఉండదు.
ఓకే సార్. అంటే
I/2 కరెంట్ డివైడ్ అవుతుంది. రెసిస్టర్ లేకపోతే వోల్టేజ్ ఎక్కడి నుంచి వస్తుంది?
ఓకే సార్. సార్ ఇంకొకటి సార్, ఈ మనం ఏసీ అనాలిసిస్ చేసేటప్పుడు ఒక్కొక్కసారి కలెక్టర్ టెర్మినల్ డైరెక్ట్ గా మనకి మధ్యలో రెసిస్టర్ లేకుండా డైరెక్ట్ డీసీ ఉంటుంది సార్. ఆ డీసీ మనం ఏసీ అనాలిసిస్ లో గ్రౌండ్ చేస్తుంది సార్, అప్పుడు అవుట్పుట్ అనేది 0 అవుతుందా లేకపోతే ఎట్లా సార్ మనకి?
అవుతుంది. కలెక్టర్ దగ్గర తీసుకుంటే 0, కానీ ఆ కామన్ కలెక్టర్ లో అవుట్పుట్ ఎమిటర్ దగ్గర తీసుకుంటావుగా, ప్రాబ్లం ఏముంది?
కామన్ కలెక్టర్ కదా సార్ అంటే ఒక క్వశ్చన్ ఉంది సార్ అది మీకు
ఇప్పుడు
send
అది
చేశాను
కలెక్టర్ ఆల్రెడీ గ్రౌండెడ్, అక్కడ అవుట్పుట్ తీసుకుంటే జీరోనే, కానీ అది కామన్ కలెక్టర్ లో ఎమిటర్ దగ్గర తీసుకుంటాం కాబట్టి ప్రాబ్లం లేదు.
కామన్ కలెక్టర్ కదా సార్ మామూలుగా అది మనకి ఇట్లా కామన్ ఎమిటర్ సార్, కానీ అవుట్పుట్ వచ్చేసి మనకి రిజిస్టర్ లేదు సార్ ఆర్సీ, అది ప్రాబ్లం అయింది. మీకు ఇంకొకటి సార్ వాయిస్ బ్యాక్గ్రౌండ్ డిస్టర్బెన్స్ వస్తుంది సార్. హలో సార్, ఈసారి ఈ ఒక్కో ఏసీ అనాలిసిస్ లో మనకి ఎమిటర్ టెర్మినల్ వచ్చేసి ఒక కరెంట్ సోర్స్ కనెక్ట్ చేశాడు సార్. కరెంట్ సోర్స్ కి కనెక్ట్ చేశారు.
కామన్ బేస్ లో చేసాంగా.
లేదు సార్, లేదు సార్. ఈ కామన్ ఎమిటర్ లో మనకి ఇది కరెంట్ సోర్స్ ఎమిటర్ కనెక్ట్ చేశాడు, అవుట్పుట్ వచ్చేసి కలెక్టర్ దగ్గర తీసుకున్నాడు, కానీ మనకి ఏసీ అనాలిసిస్ లో అది ఓపెన్ అయిపోతుంది కదా సార్.
ఓపెన్ అవుతుంది కరెక్ట్. దాని అక్రాస్ కెపాసిటర్ ఉండాలి,
కానీ కెపాసిటర్ లేదు సార్. ఒక
ప్రింటింగ్ మిస్టేక్ అయి ఉంటది. దాని అక్రాస్ కెపాసిటర్ ఉంటేనే ఎమిటర్ గ్రౌండ్ అవుద్ది.
లేకపోతే మనకి ఇన్పుట్ రెసిస్టెన్స్ వచ్చేసి ఇన్పుట్ ఇన్ఫినిటీ
వోల్టేజ్ గెయిన్, అవుట్పుట్ వోల్టేజ్ గెయిన్ జీరో. బ్యూటిఫుల్, కరెక్ట్, అంతే.
ఎస్ సార్, అది
కరెంట్ సోర్స్ మనం బైపాస్ చేయాలి
సార్. ఇంకొకటి ఏమైందంటే ఇట్లా మనకి కామన్ బేస్ లో వచ్చేసి పాజిటివ్ గెయిన్ వస్తుంది కదా సార్.
అవును.
అయితే ఒక ప్రాబ్లం ఏమైందంటే సార్, మనకి ఈ స్మాల్ సిగ్నల్ అనాలిసిస్ చేసినప్పుడు రెండు పాతులు పాసిబుల్ అవుతాయి సార్. ఒక పాతు గుండా వెళ్తేనే మనకి గెయిన్ తక్కువ వస్తుంది, కానీ నెగిటివ్ గెయిన్ వస్తుంది సార్. సో ఆ పాతు గుండా మనకి కామన్ బేస్ లో యాక్చువల్ గా హై వోల్టేజ్ గెయిన్ ఉండాలి, కామన్ బేస్ లో మనకి హై వోల్టేజ్ గెయిన్ ఉండాలి కదా సార్ అది.
అవును.
సో ఒక పాతు గుండా వెళ్తేనేమో గెయిన్ పాజిటివ్ వస్తుంది, హై గెయిన్ వస్తుంది. ఇంకొక పాతు గుండా వెళ్తేనేమో గెయిన్ నెగిటివ్ వస్తుంది, తక్కువ వస్తుంది. సో ఇప్పుడు మనం
ఇంకో పాత్ వచ్చి రాంగ్, అది
లేదు సార్. ఆ పాత్ పాజిబుల్ అవుతుంది, గ్రూప్ లో పెడితే అందరు కూడా అదే చేస్తారు సార్, కానీ అందరు నెగిటివ్ అంటారు. నేను వేరే పాత్
లేదు, ఆ పాత్ నువ్వు నాకు పెడితే నేను చెప్తా కదా తప్పని.
ఓకే సార్, అది మీకు సెండ్ చేశాను సార్, మీరు వాట్సాప్ లో చూడలేదు, ఒకసారి. ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్.
రైట్,
థ్యాంక్ యూ వెరీ మచ్.
Yeah.
Sir, that differential amplifier is a part of op-amp. Means in op-amp we are giving two input. Means it is internal structure of op-amp.
Yes.
And that huge circuit you drawn on the first day is stages of op-amp.
Yes.
Okay. And sir, I have a very doubt that you have explained many times that differential amplifier, how one is giving a negative, how that is one is.
You are not giving negative. You are giving only one voltage with respect to the emitter. If you measure, see, I am having 2 volts. What are the ways of writing 2? 2 can be written as 2 minus 0. 2 can be written as 2 minus 0. That means if I have 2 volt, and I am connecting it to ground, then 2 minus 0 is 2. But there is one more way of writing 2. That is 1 minus of minus 1. That is also 2. So how you will get 1 minus of minus 1? It is only 2. I am having 2 only. But I want 1 minus of minus 1. 2 sin t. This 2 sin t, I will give it to 2 resistors now. This is in the middle. Now here I am getting 1 sin t. Here also 1 sin t. 1 sin t. Because 1 sin t plus 1 sin t is 2. But if I take this as emitter, and if there is a person here who wants to measure his voltage with respect to emitter, and there is another person who is measuring here. So for this person with respect to this, he says I am 1 volt up. This person says I am 1 volt down. What this person will say, "Arey yaar, this is 2 only," because the difference is 2. Are you getting?
So means that the person on the left and the right are the input, Vin.
Are the BJT base terminals with respect to the emitter. If one VB is 1 sin t, another VB, this is B, no, with respect to E.
Okay, yes.
So transistors are not like this. They are like this. One fellow is seeing this side, one fellow is seeing this side, no? Between you are connecting.
Yes, sir. So then
Are you getting?
So then you said the left side will be negative.
If the left side is positive, the right side will be negative. 1 minus of minus 1. If left side is minus, outside is plus. So it will always be seesaw. the height is always 2 volts. But
So then-
if you
How we will know that which side is the negative side?
he does not know, signal you will give. Transistor will tell, Arey, I got 1. This fellow will tell him, I got 1. What did you get? He say, I got -1. Signal how much you applied? 2. One will take 1, the other will take -1.
Oh, means if we are giving input signal to the
If you
left
give
side,
one apple as input, that fellow will cut, chuck, he'll cut in the middle. Half he will give to one, another half he'll make ulta and give.
yes, sir, that I understood. Means if we are giving Vin to the left transistor,
With
then it will-
respect to emitter, you have to measure. With respect to the emitter. Because transistor, emitter is connected only to this point, no?
Yes, yes.
With respect to emitter, this is 1. With respect to emitter, that is -1.
Okay, sir.
It is like a center tap transformer.
Yes, sir, that I understood. One will go up, other will go down.
Then what will happen now at the output? If one is a minus GMRC by 2, other will give you plus GMRC by 2, no?
Yes, yes.
Then when you take difference, you'll have minus GMRC. If there is any noise n here, there is the same noise n. Common mode noise will get cancelled if you take a difference. That is common mode rejection ratio.
Yes, yes, I'm just scared that if means we are taking this half circuit and then calculating the gain. So if
That is a circuit analysis technique. Instead of calculating left side, right side, take difference. Because when you calculate left side, you are getting half. Right side, you are getting another half. When you take difference, you are getting full, no? That full signal you are getting for a common emitter also. What is common emitter? It is half circuit of this. So then they have framed a network analysis technique. What is the technique? The gain of half circuit. Adha circuit, you give pura signal. Or you take a pura circuit and give adha signal and take difference. The gain remains unchanged.
for that half of signal we are giving 1 plus and
Full
other
signal we are
minus.
giving to half circuit. Complete 2 sin T, you will give it to 1 BJT. In differential amplifier, 1 BJT, 1 sin T, another BJT minus 1 sin T.
It means even we are taking half circuit, then also we are taking input full signal. So there will be no
Full
difference in-
signal, that is why gain is same.
Okay. That I was scared that if I will take the wrong side, the wrong half, then my gain will be opposite sign.
Left side is 180 degrees phase shift.
Pardon, sir?
Left side is minus GMRC by 2. Right side is plus GMRC by 2.
Okay, sir.
Okay. Next.
Hello, sir. Hello, sir.
Yeah.
Page number 12. Sir, means up to 5 volts, after 5 volts, how it will be constant, sir?
Zener V0 is nothing but Zener voltage.
I see.
Zener is constant, so V0 is constant.
Okay. For all the problems, not constant. For previous problem.
Previous problem, no Zener, so it keeps on going till saturation.
Oh, okay, sir. Sir, 11F.
नमाज पढ़ लेता है
हाँ आज मेरे तो अभी
हो गया तेरा
तू पढ़ लेने
Yeah, tell me.
Sir, in this super code, how will you apply, sir?
Don't give V in. If you don't give V in, with IP and IN, what you will get? IN into RF, no?
Yes, sir.
Don't apply IN and IP. Apply only V in. You will get 1 plus RF by R1, no? That is superposition theorem.
V9 and 1 plus
V in
RF.
separately, IP and IN separately.
Okay. IP line and separate. Sir, for another problem you take in IN place IOS. IOS iOS
If there is RF and R1, then iOS will come.
RF and R1.
If there is a parallel RF and R1 compensation resistor, then iOS will come into picture.
In a non-inverting or inverting, any place also. Non-inverting or inverting terminal, any place. RF
parallel R1 should be connected only to non-inverting.
Only non-inverting. Oh, okay. Then in that time, RF into IOC income. Non-inverting RF parallel to R1 only I notice only.
Yes.
Sir, 22F.
Yeah.
Sir, in this Vout equal to RF into IP minus IN, this is how formula.
That you have to see subtractor class.
Subtractor.
RF amplifier subtractor you see. Derived.
Without error, less than without error without compensation means how will sir?
Without compensation, error will be more. వెంకట్ అది ఎవరో చూడు వెంకట్ అది పార్టిసిపెంట్స్ కొంతమంది ఏదో పాట పాడుతున్నారు కొద్దిగా మ్యూట్ చేయ వాళ్ళని యా టెల్ మీ
sir without error without compensation
without compensation is RF into IN. With compensation it is RF into iOS.
Okay.
Next.
Hello, sir.
Yeah.
Sir, could you explain the purpose of level shifter, sir?
Purpose of?
Level shifter, sir. You have converted the C ampere to the current Miller level shifter, no, sir?
Level shifter is only to block DC.
Sir, but in that you wrote something, sir. I missed the class. When I see the diagram, I didn't understand.
No, DC calculation you have done, no?
Yes, sir.
DC 7 volts, DC we have to block, that's all. AC if you give, then same signal is going to come for AC. AC part, I wrote something like this. This is the transistor, no? Here we have one more transistor. So if you give 0.2 sin omega t, I said I'm going to get 0.2 sin omega t here. AC is going to pass. The reason is this is in mega ohm. This is in kilo ohms. So if you have kilo ohms and mega ohm, then where signal will be dropped? It will be dropped only in high resistance, no? So AC is going to get passed. DC is going to block. DC is only by drop. 0.7 we have to take IR here. What is your doubt? DC or AC part? Yes.
Hello, sir. Hello, sir.
Yeah.
33F page number. Sir, in this Vout 1 equal to 10V in how, sir?
Because gain is 10, no? Output by input is gain. Or output is gain times of input.
Sir, in 38 page number. 38. Sir, previous one. 37. Sir, in the 1 to 3 equations, what I not understand. Sir. IOP equal to 0.
No, op-amp draws no current, no, because the input resistance of op-amp is very high.
Yes, sir.
V0 is AVD because output resistance is 0. When these two voltages will be same, when this is 0, no?
IOP is 0 only when RD equal to. Sir, we draw with AVD when only RN and R not given.
Yeah. If R0 and RN are given, then only we have to draw this.
Okay. Thank you.
Yeah. Anybody else? Okay.